YouTube desktop, yes.
So, sorry for the delay. This talk, I hope that everyone feel free to interrupt me, ask questions, maybe even get me on another topic. We worked on the slides last week and today, but today is an incredibly hot day. It's the hottest day of the year. It's tropical, and I got into trouble with my slides. Basically, I have 250 slides and I'm not going to show them. So I had to cut them down to a manageable size. Giselle is also ready to jump in and help with some of the presentation. Because what we're going to talk about is mostly the work that we've been doing since 1981, and especially when I met Giselle in 2008. So that's the last 14 years we've been working on the concept of Smalltalk hardware, self-hardware, and rewriting all the Smalltalk software and the virtual machine from scratch to work on that kind of special hardware. I'm Merik Voswinkel. I'm 58. I've been an independent researcher, scientist since I was 18 years old. I skipped going to university. I was already working at the Dutch department of CERN before I went to university, and I thought it was actually not that needed to go, and my professor was agreeing with me. So I'm, as you call, an independent researcher like they had in the 1600s before we had universities. I worked on many things: physics, computer science. To me, computer science is the science of processes, as Strachey and LNK like to point out. The research that we're doing basically was funded by my first internet provider that I started in the 80s, 1987, when we connected the first internet connection between Amsterdam and America. I had a couple of internet providers, and those internet providers basically are the ones who fund doing the research on Smalltalk hardware. And the picture that I'm now showing is that the latest name of that internet provider. It's an internet provider that builds both electricity systems and fiber optic networks. And the routers at every node of, you see a bunch of blue lines on top of the map of Amsterdam and a small city where I am now. It creates automatic infrastructure with a CAD system. We call that software-defined networking. And it's done on a supercomputer that is a Smalltalk computer running Smalltalk software. So on every bit of the crossings and nodes where all these houses connect, there should be a router, a Smalltalk router running Smalltalk software. I'll get back into that later. So as a scientist, I see the world as built out of systems. The universe is a system, complex Earth, how it was created 4 billion years ago out of accreting dust, creates a very complex system that where both the geology and the weather systems and the energy systems and the life systems all interact in one complex system. We ourselves, our system, we're made up of a whole bunch of systems. We have social systems, that's in the middle, in the background, that interact. And on the right, there's the self-portrait of the internet, which is the largest computing system that we've built so far. And we try to build our Smalltalk hardware and software to extend that internet system into a next step system that we call Ethernet, which stands for the intertwinement of an energy system and a data system like the internet and all computing hardware. To work on our project, we got the main lesson from LNK, where he describes how in the 70s they did a Wayne Gretzky game of invention. Actually, I should not talk about that and let Dan Ingalls, who was in the meeting, talk about that because he was there. I'm just trying to tell the story as Alan Kay describes it on his many lectures online. Wayne Gretzky was the best ice hockey player in history. By orders of magnitude, he scored many more points than everybody else. When they asked him, why do you score so many goals, he said, no, because you miss 100% of the shots you don't take. And that basically meant, no, why not score try to score every time you can. You might miss a whole bunch of them, but you still have a lot more chance to actually take a lot of scores, which he did. When they asked how he did that, he said, now, a good hockey player goes where the puck is. But a really great one, like he said, like Wayne Gretzky, he goes to where the puck will be in the future. And that is the metaphor we use for the Wayne Gretzky game of invention, where we like to start with a very simple idea, say 30 years out in the future, as Alan Kay said, take some cosmic goodness intuition, take some idea that what really, really good to have. For example, having computer systems, our computer chips, and solar, that's the main source of energy nowadays. Have those things in 30 years from now, we'll probably be able to grow them. Not just manufacture them for a couple of euros, but probably grow them like we grow plants. I'll not go into the details right now, but think of, you take carbon dioxide out of the air, you break the oxygens off, and you now have a carbon atom, and with it you build atom by atom, you build carbon nanotubes, you build wafers, you build solar panels, and you build computer chips with transistors on them. Maybe in questions and answers we can go into how that's done, but that was already explained by Richard Feynman in 1959 in his famous lecture, There's room at the bottom, and he meant there's really lots of room when you start building things directly out of atoms. And that's probably in 30 years how we can grow our computer systems and our solar systems on a grand scale, and it will be really cheap to do. Now, the Wayne Gretzky game said, so let's take that big vision of what we could have in 30 years, and then let's find a favorable exponential and see how we can go to that future. We don't yet know which technology we really need to get to that future in 30 years, but we can envision a way that we can scale things up to that. And the third is you take that cosmic intuition 30 years out, and would it be ridiculous if we didn't have that in 30 years? No, it would not be ridiculous with the knowledge and the science that we have today, that we could build such a system in the future. It's just we don't know how to run the software, how to do the simulations, how to make all the atoms exactly fit, how to run software on computers that will have flaws in them. But those are problems we can solve in the next 30 years. So, so you take that 30-year idea and you take it back to 10, 15 years out from now. So 2032, 2037, can we build that thing then? And I would say, yes, we can build that then. We can envision making some grains of dust that have lots of transistors on them, and you throw them in a bucket, and that together is a supercomputer. And we probably can make them for a couple of cents each. So you put a few euros worth of sand, structured sand in a bucket, and now you have a supercomputer. And it probably can run on solar energy. But actually with Moore's law and with our facial exponential, we could actually build that already today. You just run Moore's law in reverse. Is there anybody here who doesn't know what Moore's law is? The idea that every 18 months or so we'll double the amount of transistors we can build, or we in 5 years time we can double the quality of our solar panels. So if that goes on year after year, you get a doubling every couple of months or every couple of years. And it gets cheaper every time we double. Now, it can also be run in reverse. If we want to build that system today, it would be very expensive. Think of 50, 100, 200 million euros. But we could build it today and have that computer of 10, 15 years in the future. And we need that today because then we can start building the software for it today. It's going to take us a long time to make the software to run on those future computers. So let's make them today by building a really expensive computer today. That's what Alan Kay and Dan Ingalls and the team at Xerox PARC did in 1972. They built the Alto computer, almost a supercomputer in 1973. I think it was in today's money something like $80,000 for each computer. And it was like the Macintosh of 15, 20 years in the future. And they already had it now in 1973. So they could start writing the software for it. And everybody knows that software because that's what we use today on our laptops. I don't have to tell that to small talkers, but lots of people in the outside world still don't know how that software got created. So we'll build ourselves a supercomputer today. It's going to be expensive, and we'll run that software of the future on it. In 10, 15 years, it will be finished. And then we'll have the beginnings of our 30-year out computer where these things will be really cheap and ubiquitous. So right now, we can start writing that software, invent that software. That's step 7 on our slides on the supercomputer we have today. And if we do that, we can do 2 things. We can, that's the first slide, we could create that software of the future right now rather quickly and simply because it runs on a supercomputer. So we don't have to optimize it. We just write it quickly in an afternoon and test it. And Alan Kay's team at 3PRI has been demonstrating that between 2006 and 2012 by writing almost a complete operating system for a personal computer in 20, 30,000 lines of code instead of the 200 million lines of code that were used to build a Windows or a Macintosh or a Linux system with. The other thing you can do is you can already make that software of the future today on our supercomputer, but then we do have to optimize today because that software does not run very efficiently yet on our supercomputer. So we would have to add a couple of years work to make that run really efficient and fast. But in our first step, we said, okay, but we don't have to do that. We can also just write software as Kleenex, as tissues that we use for a couple of hours and then throw it away and write something new to see how that future software should be. So that's what we started to do in 2004, 2008, when Giselle and I met. By then, Giselle had already been designing microprocessors and computers for many years and developing cells and Smalltalk variants for it. And I had started in 1984 building supercomputers. The one got published on the front page of Byte magazine, sadly without my name on it, but it was still my supercomputer. We built large supercomputers with it, and that's in 1989, something like 1,000 processors that each were capturing the data from the Large Hadron Collider. Actually, not that particular one, we had the previous model, but the point is we had a supercomputer just to get a few gigabits of data per second. And in those days, you could not do that with a personal computer. You had to build supercomputers. I made the mistake in those days to try to build a parallel C compiler on it. But I had seen 1981 Smalltalk and I thought that's going to be the software that's going to be running on my supercomputer. And although I didn't work on it for all those years, I did try to start building my own Smalltalk, but then a parallel Smalltalk from 1983 onwards. Basically, I'm still working on it. We got some versions working, but no, we'll get into that later. So we had a team, and the name of that group, we have adopted the name Morphle, based on the morphs that we have on our Squeak desktop that were invented in the Self software system. So it's a precursor of that's going to be what we build our GUIs with. What we really want to run on it is operating systems and GUIs like Croquet, which is a system that Alan Kay started working on with his group in 2002. And think of it as, today we call it the metaverse. Sometimes people said it looks like Second Life, but what it really is Douglas Engelbart's vision of, let's build a GUI on top of the internet that we all can collaborate, share things with. And right now we're using Zoom, which is a very, very bad implementation of that idea. It's just the video conferencing and screen sharing, not all the other things that Douglas Engelbart envisioned and that we later tried to implement in Croquet. We can come back to that. I just wanted to say that's one of our first applications we want to run on our supercomputers today. Now, we'll skip over this slide because we're going to come back to it. But on the slide is basically all the ideas that Giselle and I worked on in 2008 on how can we make a processor, we call it the Silicon Squeak processor, that can reconfigure itself, that can run the bytecodes of Smalltalk. That's on the top. You see the bytecode table, you see Squeak. It should run without any change on our hardware. On the bottom, you see how the inside of the microprocessor looks like. And we'll go back to how we're going to have hardware with the yellow block for the interpreter running on top of it, and running the compiler on top of it, and on top of that, we're running the Squeak image. So all these things we'll get back to in detail later. But the point is, that's our first model of a microprocessor that we build supercomputers out. Now, let's go talk a little bit about hardware. On the bottom, you see a guy holding a square disk. That's part of a wafer that was cut out. Next to him, on the bottom in the middle, you see a 45 centimeter wide wafer. That's the largest we can produce today in the most advanced fab today. The machines for that are made in my country, the Netherlands. And they basically, you can only find them in Taiwan at the moment. And that's how you make all the transistors on we call it a wafer. And there's lots of transistors on it. And normally you take that wafer, it has a regular pattern of squares on it. You chip the wafers. And if you chip the wafers, then you get computer chips. Except our supercomputer is the project that we've been working on at least since 2001, is we won't chip our wafers, we'll keep it intact, like you see on the right, but we'll keep it completely intact. So in our case, it will be just a rounded wafer. And on that wafer, if we use the current, we call that the node, the current size of transistors, something like 5 nanometers or 3 nanometers, and we put them on those large disks, you get to the number at the top. I hope everybody can read it because I can't. There's something obscuring it from Zoom, but probably you can read that we roughly can get between 10 to the 13th and 45 to the 13th. So that's 45 times 10 to the 13th. So to put it in words, 45 trillion transistors on it. Now, that number is not really a hard number. That is, it could turn out that after we make our prototype, it turns out it's only 32 trillion. It might actually be 55 trillion, but it's a ballpark number of, it's a huge number of transistors. Now, the largest computer chip that introduced 2 months ago was by Apple. It's called the M1 Ultra. It's in the Macintosh studio. And that chip is right now, I think, the largest chip you can buy. And that has over 114 billion transistors. So 45 trillion transistors, that is 500 times larger, if I guess correct. So that's on a computer disk, you can have up to 2, 3, 400, 500 computer chips. That's what Apple does. They cut them in small pieces. we keep the disk intact. So our computer chip is basically 500 times larger, and give or take a million. For those who have problems with those large numbers, it's like having 45 million times a million transistors. And in our case, we'll have something we'll talk about later, optics on it, actually very special free space optics on it. So that's optics, light coming from the disk to communicate. It's not even going into fibers, but it's going through the air or through water. And if you add all the gigabit links we can put on that disk, you could actually get to 140 exabits per second out of one of these disks. So that's not the Wayne Gretzky thing 30 years from now. That's a thing we can make today. It would be very advanced. It would be more advanced than the existing one that the guy is holding in his hand. You can buy that one today for 2-3 million. But actually the price to make one of these disks is more in the order of 10,000. So that's what you can do with what we call wafer scale integrations. That comes from the older word, an integrated circuit. Those are the computer chips we had in the 70s. And we now have wafers that have integrated circuits. And that's why we call it the wafer scale integration. If you start doing these things, you have to know a lot about physics. I won't go through the whole list, but I'll pick a few things out. For example, if you want to communicate on 1 bit between 2 computer chips, it's something like 1 to 20 petajoules you need in energy to send that bit. If you, it's more on the bottom, put something in memory, we call that the DRAM cell, then it's something like 10 femtojoules. That is roughly 1,000 times less. Switching a CMOS gate, if you build the very best in the world, that is something like 50 attojoules. That's another factor of 20 to 100 less in energy. But one of the big problems, you see that on the top, internet, optical, DWDM links, that's the things that go in submarine cables. That right now is more in the order of 3 nanojoules, which, if I guess right, is 1,000,000 times more energy than it costs to flip a transistor, or 10,000 times more than to put it in a memory cell. And we're quickly going to go to the hardware, and there we see that we'll use the third one from the top and the top 2. So we're actually going to have internet access right now at 40 to 80 nanojoules per bit, and wireless is even more expensive. It's 30 microjoules. That's 1,000 times more energy for wireless. And to put it in fibers and route them, you talk about 20 nanojoules. So those are more than 1,000,000 times, several orders of magnitude more energy than you use on a computer chip or in a memory cell. So the main problem that I already have is I'm going to build these large wafer scales. That's just a thing we print out with our computer, send it to Taiwan, and they make it for us. So, making the design is hard, but it's much harder to run that wafer. If we switch it on, it will have so many transistors on them, and they all use these femtojoules that I just talked about. If you add that up, you'll basically melt your wafer. So that's a problem. We need to solve that. And one of the ways to solve that is to take all the communications between the computer chips and do them in optics. And the way you do that is you do that right now. And imagine, for example, standing in the room with somebody else in the room 10 meters apart from you. You put your hand or your glasses for your eye, and you look in the other person's eye. At that point, you're basically communicating, sorry, I have a dry mouth. You're communicating with 1,000,000 channels of light between your eye and that other person's eye. So if you do that in a computer chip, or in our case, our wafer, imagine having 1 millimeter by 1 millimeter. That's just as large as the retina in your eye, maybe a little, maybe 5 times larger or smaller. It doesn't really matter that much. And you pattern on that 1 square millimeter. You pattern these transistors and light sensitive diode kind of a thing. You picture there. You put some lenses on top of it, also very microscopically small. Then you could easily get 1,000 channels on 1 square millimeter. And we have 450,000 square millimeters on our big wafer. So that's already a few million to a few billion of channels. And each channel can do at least a gigahertz per second, and a gigahertz per second times a billion. Then you get to these large numbers of petabits and exabits and whatever. So our computer can go really fast, but we have to build it specially, otherwise it will melt. Here's how you actually do that. It's probably too hard to see, so ask for my slides later. But on the bottom, we have a tiny little, the bottom layer, we have a tiny little transistor drawn there. And on the right, we have added 2 photodetectors against the transistor, and they're the same size as the transistor. So you can build tiny little photo optocouplers, we call them, things that capture a couple of photons and translate that into an electron that will flip your transistor, that switches the transistor. And you then build that on the total top layer of the wafer, and then you have lots of arrays with think of it like small mirrors and pieces of glass where you reflect all those free space optic channels to each other. And you can have 2 wafers communicate with each other, or you can have one part, say the left part of the wafer, talk to the other part of the wafer at speeds of millions of gigabits per second. Now, another problem I already told you is it's going to get really hot, even if we add all those photonic things and light switches and stuff. Then we got rid of 1,000 times the energy, but we still have enough left to heat the wafer really badly. So we'll have to immerse it in water. And I probably don't mean real water, but let's say a liquid that starts cooking when you heat it up to 40 degrees. Like alcohol, for example. Alcohol is a liquid that boils at a lower temperature than water. And then it goes up the top in a copper coil. You see that in the top circle. And there the droplets and the bubbles coming from the cooking surface of the wafer will hit a copper coil. And there it will heat a lot of water. And that's why we're going to put in the future our wafer scales in a liquid. And then the wafer scale will heat the liquid, and the liquid will be used to heat your house, your shower water, heat up the water on your cooking stove, and brew you a cup of tea. So that way we can use our energy. It's not wasted. We don't have to cool our energy and send it out into the sky. Instead, we use it to heat our houses and run all our other energy needs where heat is important. You see here a couple of, think of them as refrigerator-sized underwater computers. And on the bottom, there's one guy standing next to that single wafer scale immersed in water that we saw the first man holding his wafer. That's actually our competitor. They did the first wafer scale. Giselle and I hope to be doing the second wafer scale in history of humanity. I'm going to quickly go through this. It's basically saying, okay, we're going to use it to run the entire internet. So we're going to use them as the optical routers, the Morphle wafer optical router. It routes photons and electrons and also guides atoms from hot water around. It's basically, think of it as a distributed data center, but it's not in a data center. It's every house in the street or a city has it in its house as a heating element. and they have a fiber with the neighbors that go to the internet exchange, and that means that these wafers can communicate with all the other wafers, and that's what we tend to use to call as a cloud computer. So it's basically a distributed cloud computer, distributed because it's in everybody's home. So you heat the house water with it, you run it on solar energy, and a tiny little silicon squeak processor that we won't talk that much about today, but we'll also make a tiny version of the wafer scale, and that will charge some batteries and manage the solar energy. It will interconnect houses into what we call fiber hoods. If you Google that, you see that Google does that, and our company does that too. We have the trademark on the name. Google is allowed to use our name to build their own fiber hoods with it, but they don't use our special router interconnect system. So if you are at home and you have 50 hops between you and the center of your country, and then that's where there's an internet exchange, that's short for IX. So there's an internet exchange where your internet will go to, it hops through your neighbor, and then it hops to the next city and the next city, and then it arrives in the center of your country. And it'll be something like 100 hops from anywhere on the planet until you arrive the Amsterdam Internet Exchange that I helped found in 1996. And in the same way, I just helped the Ukrainian government with disconnecting their entire internet from Moscow and connecting it to that same Amsterdam Internet Exchange. So one of the things is, if you have your computer in your house connected to the rest of the world, the people who run their software on that computer don't want the people in your house and your neighbor's house to spy on what's communicated over those optical fibers. So we built the onion router into the hardware of the processor chips. So that's a program that wasn't written in Smalltalk. That's a program that was written in C++. And I have almost finished rewriting the onion router in Smalltalk. And it can now run on our software, on our hardware. And it gives you 3 to 6 layers of encryption for all the packets going to this cloud computer system. We'll talk later about this system, the Morphle optical router, or the Morphle wafer scale, the supercomputer. It runs a couple of types of software systems, like Silicon Squeak, x86. Think of a virtual machine that they run in a data center. That will be completely emulated by our software, the same way as currently you can run an x86 on a ARM processor from Apple. The M1 processors can run x86 code as well. And Silicon Squeak is our native Smalltalk processor. It can run that. It can run RISC-V, and basically you can adapt our hardware into running any type of microprocessor that you like. We do that with the next line, the reconfigurable Morphle Logic. That's like a field programmable gate array. It's a sea of gates. The difference is that we, with Morphle Logic, can change the pattern of the hardware a couple of times per millisecond, and we can basically rewrite the entire wafer scale in a fraction of a second to be a completely different computer, while the software is still running on it. We'll come back to that later. So I can't see my own slides. So there's a because it's Morphle Logic makes the thing reconfigurable. This microprocessor doesn't go out of date in 5 years, because we basically can reprogram it to be a different future microprocessor and be compatible with that. So it can run a much longer time. It won't go too slow, and then you want to buy a new one. You can run it as long as it keeps functioning. And when it gets little defects in it, we'll fix those in software. So instead of throwing your chip away after 2 or 3 years, you keep running them for as long as it works. And nobody knows how long that is, but it's probably something like 10, 15 years that you can keep this thing running before it breaks too much. We'll skip the last 2 lines, because basically You can put a virtual machine running on the wafer. At a certain point, the sun will go down. There's no cheap electricity anymore, and at that point, we'll just move the software to another continent where the sun just got up, and that's much cheaper than keeping it running all throughout the night on batteries, because basically it's the full cost of running a supercomputer is not so much the supercomputer. That's only 10,000 euros. It's running the energy that's so expensive. So we'll do that with solar energy mostly, because that is over 21 times cheaper than any other form of fossil energy that we have. And for the future, we'll actually build Matroshca Brains out of them and have the whole sun output be absorbed by a supercomputer, but that's probably 200 years in the future. So on those wafers, there's a whole bunch of cores. Think of it like 1 million cores, but because you can reconfigure them, you can also reconfigure them as GPU cores or as systolic arrays doing neural networks. It's basically a reprogrammable system. So the number of cores isn't really fixed. And there's a lot of SRAM on it, probably something in the order of 500 gigabytes of internal SRAM on the wafer. And I show 3 diagrams here. Basically, the most interesting part is there's a network between all those cores communicating, making all these processors work together. And on the bottom right, the yellow one, you see what happens if one of those processors would be damaged. Then you just rewire the wires. That's the Morphle Logic technology that reconfigures itself. So you just go around the bad part and the rest of the wafer can keep functioning. So lots more wiring diagrams. Here's a way to build whole groups of wafers together. This is a tiny bit of a chip that zooms in on what's on those wafers. Here, another set of those wafers. And the whole point of that is the bottom left diagram. We're going to have these objects that are communicating with each other, and they form some kind of virtual pattern in software that maps to the physical pattern of all those cores interconnected to each other. And that's really our problem. It's not building the hardware. It's finding ways for our software to map flexibly onto our hardware system. I'll skip this slide. We're actually not going to have these regular patterns of lines between our cores and our processors. We're going to have a flexible system. Right now, the research says that the SlimFly will be the most efficient one, where all the processors get complete control to talk about with all the other processors, even if there are 1 million, and they only need to go 2 hops over a network. And to do that, you need the SlimFly configuration, and that's what this diagram tries to describe. But there's a nice paper on it. I'll refer you to that if you're more interested. So this is our problem. Up to now, we have only one circle. That's the sequential processor we run our Smalltalk or our cell phone. And now, how can we make it run on lots of computers interconnected, either on the internet, that's called distributed computing, or within our wafer scale, or between microprocessors with fast optical links? How do we map that? And with us today is David Ungar, who in 2008, when we announced our wafer scale project, he surprised us with a research project where he said, hey, I'm going to make a Smalltalk run on 1,000 cores. And he took the original Smalltalk 80 from, I think, 1996 or 7, built a new virtual machine for it, and then ran Squeak on 1,000 cores. And he tested it on a 52-core machine. And the idea there is actually very simple. Just think about Smalltalk. It's objects. We have objects that send messages. What if every object in a Smalltalk system is on one of the cores of your parallel computer? You send a message to it. If it's on your own core, it goes the same as currently in our sequential Smalltalk. But if it's on another core, You just send a message and you send the context object with it. You copy it over a fast communications channel. You can do that at 10 gigabit or 100 gigabit now. And it arrives at the other core in a few nanoseconds. And there it will now start executing. So imagine having 100 objects. They're all on a different core. I am on my own core. I write a program saying, send all these objects a message. And now, a few nanoseconds later, I have suddenly 100 processors running 100 objects on different cores. That's the most simple way of writing a parallel program. You actually don't have to change anything in your Smalltalk software. You could, in theory, scale it. In practice, it's a little bit more involved because you have to now start taking into account that certain processors will be slow and others will be fast. So you send 100 messages to 100 objects. Some objects will be quickly finished and others will take maybe hours to come back with a result. I don't have any slides for that, so I just took the video of David Ungar's presentation. He's with us. He might be probably better able to quickly describe it in a simple way. I'm just showing you a few of those slides as a reminder of what needs to happen to make the standard Smalltalk software or the standard self software to run on such a parallel computer. You keep the same interpreter and compiler, but instead of having direct pointers, it's much easier to have an object table. And in the object table, you would have things like you send a message to an object in the object table, and the object table points to either the local memory where the object is or the remote memory. And David Ungar's research had as a result that you're better off having special heaps for keeping all your objects. Some are read-only heaps, others are read-mostly heaps, and others are read-write heaps. And the point is basically that you can, in advance, distribute your objects flexibly in such a way that they don't have to be copied over the network all the time, and you get the maximum amount of processors working on the largest amount of objects. And that's where most of my research is about. You can also do a lot of load balancing. You can make the number of objects change, but you can also make their location change. You can take into account how much bandwidth there is between one core and the other. So a slow core with a slow bandwidth gets less objects sent to it than a core that's next to you. So you need a whole bunch of changes in your adaptive compiler to make all these things work automatically. And that's basically the main challenge of writing the software in the next 15 years to run on these 1,000 core and million core processor systems. This is a slide from a screenshot from the measurement of the cores. In the bottom, for example, there's a Kvyat star, that's a rounded star with 52 cores. And where there's a red peak that's where currently the processor is really working hard, and others are currently not doing anything. This was in the beginning of the research project. Later on, we have recordings of benchmarks where all the cores are running at full speed. So I could give a demo of how that looks. Are people interested in that? Hello?
Yeah, I think a demo would be good.
Yeah. Now I have to first warn, we try to get the demo to work on an Amazon F1 with 100 FPGAs and over 1,000 silicon squeak cores, but I can't afford it. It was around 900 euros to rent it for a whole day and run the supercomputer in front of us right now. So instead, I'm going to completely fake it. I'm just going to use a completely different piece of software, Squeak, running on the Truffle Squeak. That's a Java system, but it's still the same type of software that's around here. It's trying to learn from on the bottom of the top we'll have the standard current open Smalltalk VM running the standard squeak, bouncing atoms, and on the bottom we have exactly the same software, but now on top of a JIT compiler with lots of partial evaluation tricks and a whole bunch more. We'll go into the details. But if you had our adaptive compiler running on our hardware, you get exactly the same result, except at a different level. So sorry, we go full screen. So when we're starting it, on the top, we see that it's doing 58, 56 frames per second. And on the bottom is the truffle one, or growl squeak as it's sometimes called. And there it was much slower when it started up. It was only 10 frames per second. It's now a couple of seconds running, and now it's already getting to 52 frames per second. So it's getting almost as fast as the top one. If we wait a couple of minutes, the adaptive compiler for growl is analyzing all the software. It's compiling it to assembly language. It's measuring if that has enough optimization in it. If not, it recompiles it again in a different way, and it keeps doing that over and over to compile the software until it starts working twice as fast, and then 4 times as fast, and eventually 8 times as fast. And you should now imagine our software, the adaptive compiler that Giselle and I basically still are working on. That adaptive compiler would not just adapt it to run on one processor faster and faster, it would also optimize it for running on 10 or 100 or 1,000 processors. And we actually can also make it adapt in such a way that the program generates new hardware, that the compiler starts making hardware blocks that are just right for running that particular loop in that program and nothing else. It's like David Ungar's hotspot compiler, except it will be a hotspot that takes the hotspots and makes hardware blocks for it. Now, that is our research. That is what our FPGA systems and our ASICs and our wafer scale can do in various degrees. And it's very easy to run a program like this and run it on 1,000,000 cores. And then it would not be like right now, the counter says it's at 240 frames per second. So it's 5 times faster than the original squeak. But in a 1,000,000 core system, it would now be 1,000,000 times faster, plus the 5 times faster. So it would be 5,000,000 times faster. Now, that depends on which software it is and how long you run the analyzing adaptive compiler and how good your adaptive compiler is. So we'll go into that later if there's still time, because I think I'm running out of time with my talk. But the point is, you get the same software, nobody touches it, and it starts running faster and faster after it's analyzed by an adaptive compiler system. And that's basically the whole deal. I'll quickly describe a little bit how it looks from the inside. And then I think we should have some questions and maybe go into the second part of the talk, if you're still interested, where we start talking about what kind of software you need to run on such special hardware. That scales, that's the clue element of everything. It has to scale faster and faster on more and more processors at higher and higher speeds and at more and more efficient assembly and microcode instructions. Because our Silicon Squeak is actually a microcoded system, it doesn't have a concept of a 64-core processor. It has slices of, say, 8 bits. And if you need a 64-core processor, like an x86, we'll take 8 slices and make them work in a team, and then that works as a 64 processor. But you could also take 200 slices and run 1 x86 cores. And as you know, we have 1,000,000 processors, so we can easily take 100 processors just to emulate 1 x86 thread, and then we'll still have 10,000 cores of x86 super speed running at 50 to 100 gigahertz, although it's virtual. I also don't go into the details of our hardware because, for example, our hardware is mostly asynchronous hardware instead of the standard synchronous hardware that we currently have in our microprocessors. And our Morphle Logic makes things completely different. That makes it programmable and reconfigurable. And one of those things that's also important is that you see in this diagram is these blue blobs. Those are the Silicon Squeak cores running exactly the bytecodes from Dan Engel's virtual machine. So no translation necessary. The hardware knows the bytecodes that the Smalltalk compiler generates. But those blocks, they are interconnected in that slimfly network, or sometimes we call it a network on chip, to all the other cores. But the memory, the slow external memory, that is actually somewhere outside of the system. It could be outside of the wafer even. And there's also a network outside of the wafer that's going to the neighbor wafer in the house. And it's going to the wafer on the other side of the planet. That's an optical network. And there would be also a whole bunch of these blocks, these blue blocks, that change their shape or become bigger or team up. And again, these other clusters you would all find through the network. So the network is quite important in these massive parallel computers. And that's why our first piece of hardware, we actually don't call that a microprocessor, we call that a router. A router is the thing that routes between all those blocks and sends data over flexible optical networks. And we sometimes call that a switch instead of a router. The protocol it can use is Ethernet, but it also has a protocol that we can program ourselves, and we can change it while the program is running. We call that open flow, and we call that P4. That's the programmable router system that Intel at the moment is selling as a Tofino chip. That's a router that does something like 25 terabits per second. You can buy one for 250,000 euros and put it in your network. We have it right now in our FPGAs. That's the hardware that we have today. And the ASIC we make tomorrow will have something like 256 gigabits in it. There will be a $4 or $5, $6 processor. And like on this slide, you can have many of these processors interconnected into a simulation of the whole wafer scale with 1 million processors. But the best thing would be to put all those processors onto the wafer scale itself, because the network on a wafer scale is, just because it's all on the same wafer, is automatically 1,000 times faster and takes a lot less energy than if you have a whole bunch of chips interconnected. But the point is, from the software point of view, is this is what it sees. It doesn't matter if it sees computers that are kilometers apart or computers that are all sitting on the same wafer. They're interconnected through a flexible routing network. And that's what this slide is trying to say. Giselle, would you be interested to talk a little bit about how the reconfiguration of blocks under the guidance of the adaptive compiler would be, or shall we skip it for the moment? Because I'm looking at the clock and we're now an hour talking. Maybe that's a little bit much, all those technical waterfall of things I pour out. Or maybe this is exactly the moment to start talking about how you would interpret, how you would implement this in the virtual machine. Giselle?
Yes. Would you like me to show the current version, or?
Yes. So, audience, thank you for listening. Please keep from now on. Please keep interrupting us and asking us the really interesting questions. We're giving the talk for you. You might be more interested in the software part. So the slides, for example, there were actually slides of 8 years ago and 5 years ago. We're now in the 5th iteration of Silicon Squeak, and I think that we're going soon in number 6. They're all compatible. They all run the same bytecodes. They run the self bytecodes. They run the Sista bytecodes, and we hope to change the bytecodes into yet another system. when we get the chance later on implementing our own virtual machine. But the point is, they have bytecodes, and bytecodes, you can change the bytecode set while they're running. And that means they're also another lower level assembly language. And Dan Ingalls will be familiar with that because it's exactly the same as you found in the Alto in 1973. It's a microcode system in the bottom, and the microcode itself is partially reconfigurable with the Morphle Logic. And that's how we could do all these hardware tricks really well and still be completely compatible with the microcode, sorry, the bytecode on top, and have bytecode sets that look like Smalltalk, one that looks like Self, one that's optimized for Newspeak, Squeak, one that's optimized for Chorus, the future language that David Ungar is working on. There's probably going to be a bytecode for running Java and Python, and pick your bytecode and we are able to implement it. And for those who know about bytecodes and microcode, think of the bytecode is a tiny little interpreter, which is a 4,000 microcode instruction loop in the caches of the processors. So at a speed of 1 or 2 nanoseconds, it can execute one bytecode by running one microcode instruction. And they're really closely matched. So if we have 1 million processors, it runs at 1 gigahertz, you'll basically be getting the same speed as currently on the 4 gigahertz M1, where the last time I looked, I got something like 1 billion bytecodes per second to 2 billion bytecodes per second on a single core of an M1 3 gigahertz processor. So our 1 gigahertz processor would be doing 1 to 2 billion bytecodes per second times the number of cores, of course. So having 1,000 cores, that's on the smallest of our processors. On our FPGAs, it's really a lot less, but then their prototypes, it will be something like 40 or 50 processors. So you would still get something like 40 or 50 bytecodes per second on our prototype FPGAs, but on the ASICs, you would have 1,000 processors and you would get 1 billion times 1,000 is 1 trillion bytecodes per second if you write your program to do that. Giselle, would you take over?
What would you like me to show?
I'm still showing how the hardware runs the virtual machine that runs the image with the primitives, the objects, and the interpreter.
So this was the presentation that we did in 2008 to explain the idea behind Silicon Squeak. And the idea was that a virtual machine can be organized into 3 parts: the primitives, like adding 2 numbers and so on, the object memory, which allocates new objects, has the
that's the blue block on the top. On the top is the Squeak image, and there's a blue object that's OBJ. That's an abbreviation of object memory. There's the interpreter, and there's the primitives. It's a standard Squeak image.
Yeah, so the normal way that you do that, you have a translator that will translate this Smalltalk code into C, and then you compile it with, for example, GCC, and then you get the yellow blob, which is an x86 binary or something like that. So the idea was, if your hardware could accelerate the interpreter, then you could use the original code for the primitives and for the object system by running them as bytecodes. So that's the picture below. And the idea was, since we wanted to run it directly on the hardware without an operating system, so Squeak would be the operating system, like on the Squeak in OS project. The problem with the Squeak in OS project is that it's completely insecure. It's like DOS. You have access, you can do anything, you can mess around. So if we, instead of having one Squeak, we had a bunch of squeaks, where one was controlling the other ones. And then the applications the users ran in the user images, then they could mess up whatever they wanted, but they didn't have access to the squeak and OS primitives that only existed for the system image.
Yeah. So that you see on the bottom. Eh? The right one is the system image running user images for all users, or for one user that has multiple virtual computers running all at the same time. Special desktops for themselves, and also a system that basically does the hard disk and all the I/O stuff.
Yeah, so
shall I go to the other explanation of how the interpreter and object is taken over step by step? That's the earlier slides, these slides.
Yeah, that's more or less the same thing. That's the interpreter and the simulation.
Yeah, or you want to explain this, or shall we skip it?
Yeah, you can skip it. It's essentially the same slide as the other thing.
Okay, then we go to this slide.
Yeah, so the idea is that you type in some text, and then there's the compiler that will generate bytecode.
Sorry, there are a few people around who don't daily program in Smalltalk. So you type in some text, you write a Smalltalk program, a squeak program, a Pharaoh program, a quiz program, a self program. You type it in, then you get source, and then you compile it.
Yeah, and then you get the bytecodes, which can be interpreted. So that's what the second level shows. If the first time that you call the code, we interpret it because we don't want to waste time compiling it in case it's never going to be used again. But if you call it a second time, then a very simple compiler, comparable to what we now have in COG, would generate the microcode. So just like it now compiles for x86 or ARM or RISC-V, it would compile for the Silicon Squeak microcode.
Or for the M1, the Apple M1.
Yes. Well, that's ARM.
No.
And then
we're now at the bottom row. We're now starting at the bottom row.
Yeah, exactly. So the idea is that if you have a piece of code that's really used a lot, that's where the name hotspot came from, then you could have a much fancier compiler that would generate higher quality.
Yeah. So we named it inlining compiler in this slide.
Yeah, the inlining compiler will take a bunch of tiny little methods and will inline them into one big piece of code. And then this ALU compiler is for an acceleration that model of Silicon Squeak had.
Yeah, so but it could also be our Morphle Logic compiler.
In the current version, that's what it would be.
So that's where I think the magic starts. So we don't just have a very fast version of the open Smalltalk compiler that Elliot Miranda made. We also would have an adaptive compiler that would learn so much about the code that it could create blocks of hardware and compile for that. It could still use the microcode or use PICs, but it could also, in this slide, it's called ALU matrix configuration, but you could just say Morphle Logic configuration, or use FPGA blocks, or use generate new types of hardware even. Lots of things that it can compile to, and that would create the hardware as it would fit. It just depends on how smart your inlining compiler is.
Yeah, these are just details.
Are there already some known tricks for that? Like, are there patterns that you spot where it's like, if I see that, that's how I would reconfigure the?
No, normally it's just based on counters. So you count how many times a given piece of code is using. But there are patterns, for example.
Yeah. For example, this. Think of a GPU. The pattern is that basically it's just doing a whole bunch of added one vector to the other, or transform one pixel color in another pixel color, or calculate lines, just millions and millions of lines. So that is a pattern. And right now, the programmer by hand matches it to the GPU cores, but you could analyze in the inlining compiler what that pattern is, and then generate GPU cores that fit exactly that. Think about it. You could have a floating point graphics accelerator, but you could also have a fixed point graphics accelerator. Or if you see that the pattern is actually only doing tiny integers like 8-bit or 9-bit integers that are just well for a neural network, then you could reconfigure the whole bit of hardware into a neural network accelerator and not use GPU or not use floating point, and create on the current place of the wafer where you had standard cores like x86 cores or silver squeak cores, you would wipe that, erase it, and put those special neural net cores on it. So,
and is that a fast operation to do that? Is that, I mean, I guess there's some threshold that it's worth doing that. Is that the point?
There's a threshold. We get to that slide, the next slide.
Yeah.
So there's a threshold because you need a fancy compiler. It might have some pattern recognition, like saying, oh, I recognize that this is GPU kind of style programming, or this is a kind of neural net kind of style. Then it could take fixed blocks from its library, or it could generate new blocks. That's still a difficult research point, but we think we've cracked part of it by not using FPGAs, but compiling to Morphle Logic, which is more flexible. But if the compiler would have a new hardware block, so that might take maybe a second to generate completely new hardware blocks, or it could take an existing one in a millionths of a second out of the library. But now switching to that new block, that only requires the speed of writing in SRAM. So in the fastest RAM possible, you write the pattern, and the next clock cycle, it is new hardware executing its first instruction. So the switch itself is fast, but coming up with new blocks of hardware, that it has various amounts of time you need, and that's what's in this slide in the middle. The time to reconfigure, the purple arrow, that means you don't want to switch every cycle. You want to do it, say, every million cycles, because otherwise you're switching back and forth all the time, something like that.
And I suppose if you've got a lot of cores to play with,
yeah,
can you like trade them off? Like I'll do 100 of them.
Yeah. So
and
you say I still have
first is the one that I'll go with, or
yeah. So first of all, you can run your experiments in parallel. So while one part of the hotspot compiler just keeps compiling it to GPU instructions, processors, the other one can do an experiment. Let's see what happens if I run the same code. It just makes a duplicate. There's 100,000 free cores available. So run an experiment, see if it runs faster on 68-bit hardware, or see if it runs faster on 32-bit, or see if it runs faster on a neural network instead of a fixed loop with an inner loop. So, and when that second bit of hardware wins the race in who finishes first, then you say, okay, next cycle we'll switch to that new hardware. Or, and that's one of the work areas I work on and Giselle don't, you could just think of, hey, what would happen if I start running the same code on 1,000 cores, if I now run it on 1,000,000 cores? Would it still run faster, or would it actually slow down because it now has a lot of overhead for communication? So although it's not an intelligent compiler, it can still do a whole bunch of experiments and find out, okay, if I just brute force it with more cores, it's worth it to switch to that pattern. And because we have 1,000,000 cores to play with, and they're not fixed cores, they're tiny and they can aggregate into large cores, that means it can run 20 experiments at the same time and find out which experiment wins and switches to it. And then 1 second later, it's accelerated the whole thing 100 times, and then it starts running different code And then it starts learning again how to go back to a pattern. And because it has, say, 100 cores in the background watching all those switches going on, it say, hey, this is what happened yesterday when the same software was run. So then it can start predicting what kind of pattern would run the software better. So it's kind of load balancing, but then with many more parameters, many more degrees of freedom, which also means it gets a little harder to imagine it and to program it. So that's why we need 50 years to write that kind of software, to figure out how it would run from 50 years when we have not a few supercomputers, like a few thousand, but have 100 million of them. Then it would really be useful to have all that software tests done. And that means that we can start building, we call that traces, building traces of what was learned during the first hours of a hotspot thing, and then take those learning things into account when we run that on somebody else's computer a couple of weeks from now. So
it's starting to make sense. I get it now.
Right. The problem, however, is this is new type of compilers. There are not many people working on compilers, and we'll definitely have to come up with new ideas. There's this famous slide where Einstein and somebody else are writing on a blackboard, and there are a lot of equations, and somewhere in the middle is a large gap. And they're saying to each other, there's a miracle needed here. So we're at that stage that, okay, we can get a few thousand or a few million accelerations out of most obvious pieces of hardware. We sometimes call that embarrassingly parallel problems. It's the low-hanging fruit, but there will definitely be a few places where Amdahl's law will really bite us in the ass. David Ungar, who's also in this talk, actually did some really interesting work on that. For example, his race and repair thing, where what if you have 1 million cores, each want to change one line in the database? Now, instead of doing it in sequence and making sure that that if you change something in the database, it's not instantly overwritten by another core, or doing things like cache coherence. Instead, just let all of them try to change the stuff in the database, and if it breaks, then you spend another 1,000 tries to fix the error. So eventually, after a couple of minutes, the database changes die down and it becomes a stable state again. But you might have done, that's why he calls it race and repair. You might have been doing a few million changes in the database that completely were overwritten by somebody else because it wasn't synchronized, it wasn't, they weren't negotiating with each other of what sequence things happen in time. But now, if you have 1 million cores to waste, it might actually turn out that you don't have to be that accurate. You can make a lot of mistakes and just do it over 1,000 times and still wind up being very efficient compared to the past where you only had one processor changing everything. So, but that's research. We don't know yet what we're going to encounter, but it's quite similar to what happens if you, the mythical man-month, what happens if you do it with humans. You can get 1 million humans to work on creating food, and they can all do it in parallel. But you cannot get 1 million people to all make one cake, bake one cake. That is silly. You're better off having 2 people make the cake, and you can't accelerate it much more than that. You can, however, have 1 million people each make 500,000 cakes, so you can still accelerate cake making. But making one cake, you can't do with 1 million cores. So that's one of those areas. How do you recognize the difference between making 500,000 cakes or making one cake with 1 million people? That's what our software needs to learn. And we haven't done it yet. So we're working on it every day. And that's literally what I lie awake about at night. Just very curious, this is the kind of stuff you run those experiments on if you don't have your supercomputer yet. So these boards, for example, the bottom ones, you can buy them for 10,000 euros or something similar. and they have these large reconfigurable FPGAs on them. The top board was something we could make for $200. It has only one FPGA on it, but these are just prototypes. I'm going to slip a slide. Actually, they made these things in the past. Mario Vosko, if I pronounce your name right, is in this audience. He built this one, I think, in 1987. And there was one built at MIT in 1988. And what you see on the left, for example, is a whole stack of, I think there was 1,000 nodes running a very old style processor that they made specifically for this. But the point is, we've been doing this. I've been doing it since 1981. Lots of people have been doing this. You don't particularly need specific hardware. This is just standard hardware you can buy off the shelf. Now, what Giselle and I really want to do is make ASICs. That's where it gets really interesting, because this is expensive hardware. Making a wafer scale is also expensive. That's something like 500 euros for one supercomputer that sits on your desk, or 10,000 for the fastest, the largest that we can make today. That's really the state of the art. But we are also, we hope this year to also release our second chip. We already done one chip. We've done a second chip, and that's gonna, I hope, cost 3 to 6 cents per microprocessor, and it will probably have one full silicon squeak in it, and a lot of memory. Think of it like the Raspberry Pi or a much smaller Raspberry Pico, but then for 3 cents. And I'm going to put it on one on every battery and one on every solar cell. So when you have a solar panel, you're going to have 100 processors already in it in a network, and 100 processors for €3. So that's already, so if you want to buy a million processor unit, that's going to be, Giselle, help me, is that 30,000 euros? Yeah, so for 30,000 euros, you could have a million processor, say around December. It's not the best choice, by the way. We really want to do these wafer scales. And as I said, wafer scales go really, really, really high, like a million cores, equivalent to the M1 Ultra. But you can also think of programmable cores, and then you'll get something like 200 times less. But now you can make any processor you like. So sadly, we had a lot of trouble with our demo. And by the way, I also have a lot of trouble right now with getting my mouse back. Oh, there it is. So David Ungar's research you find on this webpage of the University of Brussels. It's really good papers. And we've been running the RoarVM that I showed in the beginning. That can run on 1,000 cores easily. That's what it's made for. It's a research artifact. You could run it today, except when we compiled it last week, it turns out that my Macintosh no longer runs it 16 cores. It now runs it only on 4 cores. And Giselle could only run it on 2 cores. And our other friends could no longer compile it. So suddenly our demo, the easy demo that you can do at home, failed. But the point there was, this is actually the command you would start on the command line to run it. That software basically already scales to all the hardware prototypes that I've been trying. And I can also run it on 1,000 cores in the Amazon cloud. And I've run it at best on a 10,000 core machine. So that's the first time David Ungar hears about that, that it was actually tested on a 10,000 core machine. Sadly, it was just an x86 machine made out of 1,000 10 core x86s. So I didn't particularly think that's a cool demo. I want to compile it to the first Silicon Squeak later in August. And by then I'll hope to send a few of you on this group a working piece of hardware. But the point is the software is already there. You can run it on your existing machines as well. You just need to have a C++ compiler that works well. And then you'll find out that you need to change your Squeak a little bit. It does run Squeak out of the box, but it gets into little, it trips over its thread mechanism. So it needs the process manager to change. And in this group, I would defer to Dan Ingels, who wrote that piece of software. It runs really well then, but okay, it doesn't take into account that there are possibility of 10,000 others. So a few race conditions need to be fixed. A few semaphore things need to be taken out of it. Then it really scales. And that's what David Ungar did with the SLI language and the ensemble system. And think of it like a tiny layer of software on top of Squeak, Smalltalk, doing things like add one to an array. Instead of sending in a loop 1 million messages to 1 million elements of array, you just say add one to all the elements. And if you would have 10,000 cores, then each would do only 100 additions to part of the array, and the other 10,000 cores would do their own 100 objects. They would be dispersed among the cores. And one way that was done on the Jelly Bean machine that I showed last is that you can do that with a thing called a concurrent aggregate. So you could wrap the whole array, which is spread around 10,000 cores, into an extra layer, a dictionary, a collection, the standard classes we have in Squeak. If you add the concurrent aggregate layer on top, you would not have to think about how to handle these 10,000 cores, each doing 100 updates on their local objects. So a lot of the simple, embarrassingly parallel problems you can hide in under 10 or 20 lines of code, and then it becomes really easy to do. You basically don't have to change your Smalltalk code that much, or your self code that much. Other things require really rewriting a library or a class completely from scratch, because they're really weird. There were a few of these experiments done, for example, in the Frank project, the Steps project, I should say, by Alan Kay. Vanessa in this group, so she's not here today. She worked on that. Yoshiki worked on that. They for example, Dan Ameling found a way to instead of having bit-blit, doing sequential loops for changing all the bits in the graphic system. He wrote it completely parallel as a data flow machine, which is completely hidden to the programmer. The programmer basically just has to specify in an abstract math language what happens to one polygon and one pixel. And if you describe that correctly, it gets scaled to 1 million cores, if you like. Completely transparently, you don't have to manage that. So we've already done a whole bunch of coding. They're already run on massively parallel Squeaks. We just need to now have it run on our hardware, so they all get the full benefit. Because if you run them on existing x86 parallel computers or ARM computers, it winds up being only, say, 30% efficient. So you get 100 times speed up with 100 cores, but you waste 30% of overhead of having a lot of communication going over very old-fashioned, slow Ethernet cables. But in our FPGA, you don't have that overhead. So there you could scale to 95%, meaning you could run one program with one concurrent array or one graphics loop, and it would just go not 100 times faster on 100 cores, but 95 times faster on 100 cores, and 5 cores would be wasted for the overhead. And that basically means we've already measured a whole bunch of situations where we can scale to that 1 million cores easily, and that's just scaling compared to 1 core. Now, the other aspect of Silicon Squeak is they themselves are 10 to 20 times more efficient than existing x86 cores. So you could get 20 to 30 million times the efficiency. And if you then lose 5% of that on the overhead of communication, that would not be too bad at all. One of the reasons you want to switch to Silicon Squeak is, as we talked in the beginning, they have completely different hardware that runs at much lower energy levels. They'll probably run most of the time as on solar energy at 1 cent or half a cent per kilowatt hour. That's my other research project that I actually use my supercomputer for, to calculate ways to make solar cells cheaper and battery charging much cheaper. I found a way to charge a battery, a lithium-ion battery, 20,000 times instead of 500. So instead of throwing your iPhone away in 2 years because the battery is bad, you can keep it going for 30 years and keep recharging it every day. So if you add all these things in, then the compute of Silicon Squeak processors at different energy levels is way cheaper than a data center. And we really think I can, in my simulations and my test, I got to something like 2% of the cost price of running a data center. I can run the same compute at 1/50th of the cost by running it purely on solar energy with all these processors to help me with. But the point is, it's not for everyone that you want to go to a Smalltalk Silicon Squeak computer 15 years in the future, but everybody in the world wants to have a much cheaper computer. Right now, 5%, almost 5% of our electricity use on the planet is wasted in our data centers doing Google searches and doing these facial recognition programs. So running them 50 times more efficient would mean that we would save almost 4.20% of all the energy that we're currently wasting on the planet. So that is a reason to switch to Silicon Squeak and Smalltalk software, because now comes this last really interesting bit of information. Silicon Squeak runs Smalltalk and Self and similar languages, bytecode languages, really efficient if the compiler is good and clever. Running Linux or Python on them would not be that efficient at all. That's where you can waste over 60,000 times. We actually saw a situation where you have 200,000 times less efficient than Silicon Squeak would do. And that has to do with how data centers are built, how software is built. C code might be fast, but it's actually also very inefficient. It takes more people to write it. So there's lots and lots of reasons why making Smalltalk computers and Smalltalk hardware run on solar energy is orders of magnitude cheaper in the long run. And that's really what my software project, my research was about. And to me, doing it with Smalltalk was natural after 1981, when I learned that that's the message passing system, and that's how you make real life scalable software. That's what most supercomputers in the world run today. They run message passing systems. And the best they run is a language that of the lowest level is a message passing system. And that goes for Self too, and for Newspeak, and for a few others like Erlang, etc. Except Dan Engel's implementation of Squeak is definitely one of the very, very best and efficient ones I've ever seen compared to all the other bytecode systems. So this concludes my rattling. I'm now 50% in on my talk. So it's probably a good moment to start opening up the floor for questions, because otherwise I'll spend another 90 minutes on writing Smalltalk software, like for example, building a parallel Croquet. That's one of my favorite areas. Burning the disk packs, taking all the software and write all the scientific papers written on Smalltalk and similar languages, taking all the bits of learning we did in 50 years, and then using all that to re-implement a slightly different version of the bytecodes, and a slightly different version of the VM, and a slightly different version of the Smalltalk language. And then you get this incredible scaling, and we get 5 to 7 year old children capable of programming.
Merik.
Yes.
One thing that you barely touched on, which I think is real important just to speed up the process, and that's why Giselle and you did it, was making Silicon Squeak compatible with C as one of the interpreted languages.
Now, we skipped that part because we now have made it compatible with x86 virtual machines.
Ah, okay.
Almost all the C code today is run in data centers or on your local Linux machine. And so to put our wafer scales in a data center, if you run a virtual machine or a Docker image or a Linux without any change then the customer is happy. They think they get an x86 machine, but in reality it will run 20 times faster at 1/50th or 1/10% of the energy. So to them, it's not important anymore that it could also run C code, but basically it will run C code at 80% of efficiency, but will use 10 times the cores, so it will still be 7 times faster at the same or lower energy level. So backwards compatibility, that's how we handle it. It's exactly the same as Apple handles an ARM processor running x86 code without recompiling it, without recompiling the C++ or the Objective-C. It just runs at 80% of its original speed. They use a similar trick like the hotspot compiler. So for us, we don't have to address the particulars of that anymore because we basically emulate all x86 code and all ARM code, and soon we're going to do RISC-V as well. So basically, but if you write Smalltalk code, it will automatically be more efficient. So it's only for keeping existing codes running on our hardware that we are backwards compatible. We don't run C more efficiently than x86, but we run it more energy efficient. So more questions? I can give a few more demos, but I don't know if you know.
Do you have any examples of things, or like just to tell us about things that work in practice? I mean, how researchy is it versus there's practical examples of things that are running well?
Now, I'm giving a very short answer because it's a detailed answer. So, for example, anything that runs on the RoarVM, which can scale to 10,000 cores already on existing x86 hardware, that can just write program in Smalltalk and you get your parallelism. You don't need our hardware for it. Our hardware just makes it run more efficient and faster. You get more cores. So you can already do that. The problem is, of course, that almost nobody in the world writes these programs. They still write Linux programs instead. So what Smalltalk software do you have out there that you want to run in parallel right now? Now, among us is Christian Heider, who gave a talk a couple of months ago on this meeting about his PDF parser, reader, and writer. So his PDF software, I wanted to run in a massively parallel system. I have a 300 terabyte hard disk, and on it, all the books ever written, all the scientific papers ever written in the history of humanity. Think of it at 300 terabytes, roughly, I think it's 300 million documents. Now, if you want to make a Google for that, search through all those documents rapidly, then you can now, you can get Google to do it. They use 2 data centers with 2 million computers, and then 1 week later, they'll have an index for you. And now you can sort those PDFs. If we just port the PDF reader from Visualworks to Squeak, or more precise to the RoarVM. Now, Christian, I think we're now 1 month away, 2 months away from having that run on Squeak. Then we could put it on our 10,000 or our million core machine and immediately analyze those PDFs at 1 million times that we can do today. So that's a programming effort of 1 or 2 months. Is that answering your question?
Yeah, I got you. So it's more about the kind of problems and
yeah,
those sorts of things. It is possible today, basically, is what you're saying, right?
Yes.
Okay.
And this particular one, for example, analyzing 1 million documents, my Macintosh is already doing it. My 10-core Macintosh, it just takes half a year to do it. But I just want to scale it up, and I want to use a better PDF reader. Christian Heider's is a better one. So it's just porting into another language and getting it to run. And in our case, that's now a total 9 weeks of work, I would say, for one person, and it's not full-time work. So is that useful? Now, Google spent a lot more money to port their software to a massively parallel computer. So I say 9 weeks is really, really cheap, really simple. Now, another project I'm about to run a 2-continent-wide internet provider. I have software for the router that's massively parallel software. A bunch of students at Berkeley and Stanford worked 12 years to write that software. It's called a software-defined network, or sometimes called OpenFlow. I wrote my own version in less than, I'm guessing now, but roughly 1,000 lines of code, and it runs roughly the same type of function that these students at Stanford did, except they took 12 years to write it, and they wrote something like 100 million lines of code to do it. I did it in less than 1,000 lines of code, and mine run probably, I'm guessing here, but something like at half the speed of their code. That results in a chip that will run it for 250 euros, while they run it on a piece of hardware that costs 80,000 euros. I actually know all these numbers because recently we used this technology for the Ukrainian government to do a DDoS attack filtering. That's basically filtering all the packets going to 44 million people in the Ukrainian internet. So that's 9 terabits per second in packets, running for a year. Can you look at all those packets and filter out the ones that are Russians attacking the websites and the smartphones inside Ukraine? Now, you can do that with a 80,000 costing chip that's sitting, it's actually, the chip costs 3,000 euros, sitting in an $80,000 switch. And the only 5 working models are currently at Intel's headquarters. There were 7 a couple of weeks ago when I called the Intel vice president, who happens to also be the professor at Stanford, who had all these students. His startup was bought, his students' PhD work was bought as a startup by Intel. He's now the Intel vice president. And he said in 5 minutes, oh, what you need is my switches. I'll send you 2. And then I found out that these things, they arrived at me at home. And let me tell you, my budget per year is something like 20,000 euros. So suddenly 120,000 worth of switches in 2 little pizza boxes arriving, and I had to ship them to Amsterdam and Ukraine. And they are basically almost compatible with our now 2,000, 3,000 euro costing router network. So basically I say, others have already shown that you can make a massively parallel switch and router out of the software, but I can do it in only a few lines of code, not a million lines of code, and I can run it on much cheaper hardware, and I get the same bandwidth out of it, same packets per second out of it. So, however, it's research that is probably my code will break in 2 weeks' time, and I'll have to spend another million to make it really stable. But then the Intel code with the students also was not very stable. So the point is, yeah, okay, we can beat almost all those projects with much better software and much better hardware, but it doesn't mean that it actually already is functioning on my desk. For example, I just told you my budget is too low, so I can't actually order the hardware quickly enough. I don't have enough prototypes being made. So right now, the prototypes, for example, are good enough to run an internet provider, but an internet provider doesn't run at 9 terabits per second. It only has to run at 100 gigabits per second. And that's what my FPGAs and my little ASICs can handle right now. But they're doing it with very high level Smalltalk software, not with a bunch of assembly language done by Cisco. So I still win by orders of magnitude. Yes, other questions? Juan, we talked in 2008 and 2010. I hope that your graphics algorithm, which is a new Morphic that runs, could run massively parallel. You talked with Dan Ameling. Maybe you could buy your two algorithms that currently are working, as far as I see. It's only a few thousand lines of code, and we can run it on our parallel hardware and have the fastest graphics card in the world.
Yes, well, that project, I guess you already know, is already part of the official quiz distribution. You just have to load a code package. It's working well. The current version is
it executing the bytecodes, or is it compiled to C?
It's a VM plugin. It uses Squeak slang technology. So it's Smalltalk code that gets translated into C and is now part of the official distributions of the Open Smalltalk VMs. You may be interested in knowing that a few years ago I did a pretty important project
Satellites?
using, yeah.
Satellites?
Yes, satellite images. Yes, exactly. Using OpenCL. And OpenCL allows doing parallel processing on CPUs and GPUs, and it's a very nice C alternative for that. And I did an implementation of my vector graphics engine in OpenCL, and the problem I found is that in OpenCL, the startup times for function calls are pretty high. So it is very efficient if you do few calls that do a lot of work. But in vector graphics, a primitive is very small and very quick. So there was an over 98% overhead. Over 98% of the time was spent in doing the stack preparation and the FFI, and actually the scheduling of the execution in the OpenCL runtime. That is pretty expensive. So that's why I didn't go forward with that. And the sad fact that Apple removed support for OpenCL from Mac OS X, that is a huge, terrible mistake I will never forgive.
Yep.
Because before that you had free, easy to install OpenCL support on all major platforms, even on Android, right?
Right. But graphics...
that parallel algorithms I implemented in OpenCL and I could not use for this problem of startup times are worth investigating in other parallel architectures and runtime systems.
So
right?
the embarrassing part is if you do just 4K screen, so that's 4 million pixels times 60 frames per second. So that's a thousand million billion pixels per second. Can we not just run that on 1 million cores and have it run 1 million times faster? I mean, your software, not the OpenGL version, but the standard slang version, should just run on that.
There is a separate implementation because the slang implementation is sequential, right? But the OpenCL implementation I did was not sequential, was actually parallel. So I know how to do that. The problem I see, or not a problem, but the open question is about the bandwidth of the memory access, right? Once you, at least in OpenCL, once you have over a certain threshold of processing power, usually the limiting factor starts being the memory bandwidth. So the GPU can process your stuff as fast as the memory can deliver and get it back.
For example,
so getting thousands of times faster without thousands of times faster RAM is
right. Now, the 100 cores on the M1 Ultra from Apple can theoretically get 800 gigabytes per second memory access. on a cluster of FPGAs that I could do, or now let's take that as example. So for over 10,000 euros, I could get a memory bandwidth of 1 terabyte per second, which is it's almost the same speed, but I could scale it up any way you like. So if you're willing to pay 100,000 for it today, we could already have 10 to 20 terabytes per second memory access speed. So there's no limit in your access speed. It's just currently, are we making ASICs or are we buying off-the-shelf hardware? But we have the memory bandwidth if your Smalltalk software runs on it.
Yeah, I was only talking about conventional DDR4 RAM, right? And GPUs, yeah, or multi-cores using a single channel of DDR4. I know that Apple has a different architecture and much faster RAM access times. That's very interesting. I haven't played with that.
No,
and I know that other things can be done, of course.
The reason you can play with it easier on Silicon Squeak hardware, or the Morphle processor, as we call it commercially. So the Morphle processor is just bytecode, so you don't have to rewrite anything. You already have the slow version running on your Smalltalk machine. So now you can run that much faster without using OpenGL or whatever compatibility. So you should be able to run it in a day after you receive the hardware. But the real problem is the hardware.
Sorry?
But the real problem is getting the hardware.
Yes, of course.
So right now, I would like to do a 28 nanometer wafer scale. I need 3 million for that. And we have a project running in the Caribbean and accelerating the routers on submarine cables and stuff like that, doing a few thousand internet connections on our routers. And that generates the 3 million that we need to fund the chip. And then I can replace our 250 euro chip running on our routers with a $20 chip running roughly 250 cores. Giselle, how much would the memory bandwidth for that be? I would guess something like 250 times 10 gigabytes per second. So that would be 2.5 terabytes per second for I'm guessing here 20 to 50 processors of $20. So for less than $1,000, you would get your 10 terabytes per second. GPU card running your
graphics. You're talking about the level of money of a good GPU card, and you get not only the processing power, but a much higher memory bandwidth. That would be wonderful, of course.
Yeah. Now, because our memory bandwidth is not limited to the chip, it's basically a network, as I, in many of these slides, just skipped over quickly. It's basically a network of blocks of memory. So you can scale it to how much money you spend on memory. It's not limited by the processor core. It's just limited by how much memory you want to have. And that's where, for example, the wafer scale is completely different from having small processors like the Raspberry Pi that has a limited memory bandwidth. And if you add more to them, it doesn't scale very well. But inside the wafer scale, the relative memory access speeds are 100 to 1,000 times higher because it doesn't have DDR. All the memory inside the wafer scale, and could be as much as 500 gigabytes. Even I have one model where most of it is memory, and therefore you get a terabyte of memory for 10,000 euros. So you get a terabyte of memory for 10,000 euros, but it's SRAM, it's cache. It is more than 200 times faster than DDR memory. And for a graphics processor means, I have to guess for you right now, but let's say you have that wafer scale for 10,000 euros. That's the production unit price. So it would cost 20,000 euros to put in your home. But Alan Kay keeps saying, if there won't be a 20,000 euro laptop out there, I'll buy it in a second, because it's more important for me to have one like that than have a car, a cheap car. So you could get one, and now you would have memory bandwidth in the order of petabytes per second. And that would be your graphics processor. So there is no limit. There's only a limit on when will it be in the shops. And to me, the limit is when can I finally get to spend 3 million instead of only spend the meagerly budgets like we've been doing in the last 20 years, like 20 to 50,000 a year at best to create this hardware. That's not enough, but it's more than enough to build the whole thing, except in tiny quantities. Now we need to build it in mass production, and that's why I'm working to get my 3 million funding. And if I had 50 million funding, then we get the top of the line 10,000, million core, 150 to petabytes and exabytes per second versions. The point is, it's just now limited to how many people can I pay to program. Most of the good ones are currently stopping and becoming pensioners. And the other ones, I need to pay 200,000 euros a year to get them to work on such a project. But the most important part is, 2-3 million to do a small ASIC and 50 million at the highest to do the largest, fastest, to do an M1 Ultra competitor, which would run 10,000 times faster than the M1. So that's just a funding problem now. It's no longer a technology problem. The real problem, however, is not the hardware, it's the software. We now need to write all the software again in a parallel fashion. That's the real job. That's actually what I want. If I had another 2 hours, that's what I would talk about right now. Let's rewrite, burn the disk packs, rewrite the virtual machine, Smalltalk from scratch. It won't appear much different, but the tiny little details in the bottom where the sequential is presumed needs to be taken out and made scalable in parallel hardware. But that's what you just did with your graphics algorithm, Juan. So it is doable.
On that note, can I just stop the recording at this point? Because I know that Giovanni takes time to encode all of these, and if they get too long, it's a bit difficult to get them out. So I'm not going to end the call. I just thought
I would rather also record the others. So I'll start recording myself, if you don't mind.
Yeah, sure. I'll stop this one, and then
Matthew, you can leave it. I'm just gonna make
okay.
a mark of the time. And,
okay, yeah, okay, there you're there, Giovanni. Good.
Yeah,
Sometimes in questions I get the really interesting things where the reason I'm in this group, so I wouldn't want to miss them. Because
okay, no problem. Okay, if we put a marker in, that's a good point, and then if we get some good stuff, we'll leave it in.
Yeah, go ahead.
Future things. You hear me?
I can hear you. Yes.
Hear me? Okay, so you're on a roll of all the future things. Very interesting. I love the context you've given it all from the start. But my question right now is, I've had since 1990 something IBM Smalltalk e-commerce system that's multi-tenant, and the big limitation is the IBM Smalltalk, Visual Age, or Faro, or any of the Smalltalks other than Gemstone, which uses way too much memory.
Yeah.
How do you host multiple web stores on a server with Smalltalk? It's are there any solutions today that allow me to build web apps that take advantage of multiple processors and cores?
Right. So in 2008, I used the first releases for Seaside, Magritte, and Pierre from Lucas Rangley and Avi Bryant. He did a startup called DabbleDB. I think that was the best hosted website in the world. He got acqui-hired by Twitter quickly after and killed the project, but the software is still very... So what he did was, every time somebody hits the web page, instead of having a cookie, it has a session key and immediately restarts a virtual machine just for that user. So he had 1 million users, so he had 1 million VMs sitting idle on his hard disk behind an Apache proxy, a reverse proxy. So that's the first question. He basically just had 1 image per unique visitor on his website, and it scaled easily to millions of users and separate servers. It could be all on one server, could also be on separate servers, the proxy made it all look. Now, today you have exactly the same system in CloudDB. They probably wrote it in C++, but the point is, in Seaside, it's only a few hundred lines of code. It scales perfectly. It might take you a couple of weeks to get it to work on your IBM Smalltalk. If that IBM Smalltalk runs on bytecodes, we can take 2 weeks at best and get it to run on our hardware. So I don't see any problem. It's just, are you willing to spend 4 or 5 weeks? If you're using Squeak or Pharaoh, you don't have to do anything. It's already a scaling website. There are hundreds of websites made with it. It scales perfectly. It's stable. My own website has been running since 2004. Never been hacked. Never crashed. It's a boring squeaky and a CSS HTML thing, and it runs the lively kernel on top of racked with Seaside. It took me over maybe 3,000 euros to write the whole web server hosting system. So it's a one-man project. It's not very difficult. You can get any scaling you like.
Merik, there's some problems with that approach. I'm familiar with DabbleDB. Abby Bryant, he lives actually 2 hours from where I live here in Vancouver, Canada. But he started an image and he uses the image for memory. My e-commerce system, we used an object database. We used Versant at the time. And the problem is I need to launch multiple images that access the same database with all the ASIC compliance and the transactions, so it's an optimistic.
So you spend all your time making your database handle it. I don't do that. I use Squeak itself as the database. So I don't have that bottleneck problem you have to scale your database, which is the database that you need to scale, not the Squeak front ends on the web servers.
Right. So still, I'm, yeah, okay. So running multiple images on a machine, that's, I mean,
So,
VisualWorks has their matrix or whatever they call it, but
On
it's the database and it's the multiple users in the same database. Because our database was multiple gigabytes in size.
Right. On a 28 core Xeon, I managed to run over, I'm thinking 10 years back now, I managed to run over 4,000 concurrent virtual machines at the same time, running, serving the files of the earliest lively kernel that Ingalls wrote. So it was Seaside sending the JavaScript code to the browsers running locally. This was I think the first year of the lively kernel, so it's no longer the same lively kernel. It's probably been rewritten completely from scratch. But the point is, I had no problem running it on a 28 core Linux and basically saturating the at that point 40 gigabits that server could handle. That was the bottleneck, not the numbers of squeaks I was running. Most of them were being swapped out by Linux onto virtual memory. But the point is, no scaling problems. And I can give better examples with larger numbers, but DabbleDB would be the best one to ask because he got it to the tens of thousands of virtual machines running on one host without any trouble. He just had different bandwidth than I had. I tried to scale it actually for an MPEG Netflix clone, and then every Seaside Squeak image for web server through the proxy would have to send something like 10 megabits per second per client. And then the scaling again was just limited by that the FreeBSD Unix kernel could not handle more than 200 gigabytes per server. So, but it was not saturated by large numbers, and I mean hundreds of thousands of streaming Squeak web servers behind an Apache or NGX proxy, which means it's also the Unix that got into trouble because of the constant packet, the constant thread switching going on in the Linux. that would be prevented if they just use the squeak images. But the point is, scaling is not that the problem. It's usually your bandwidth or your database or some other bottleneck.
So just one more quick question, and that is anyone familiar or aware of any kind of Smalltalk VM or capability to run Pharo or any Smalltalk on top of .NET?
On top of? No, only on top of C++. That's David Ungar, RoarVM, who's in this group. That's just a C++ program that runs on maximum on x86 or other many core machines, but I don't know what .NET would be under it.
Yeah, there were .NET Smalltalks. David Sims, I think, had S-script or S#, but they were not compatible with Squeak and Pharo.
So, but if you say .NET, I hear Microsoft/Azure cloud. So you would run the RoarVM directly on their FPGAs, the same one they use to run the Bing search engine with, and that scales perfectly. That is basically any FPGA they have on Azure or Amazon. You can with a week run Silicon Squeak on. Basically, configure the FPGAs as Silicon Squeak cores and then run standard Squeak software on it, and get terabits per second out of those FPGAs. These FPGAs are really fast and expensive, except you wouldn't want to buy them really expensive.
Quality.
Sorry?
RoarVM production quality in its current state?
Ask David Ungar, I would say no. It runs really stable, but there's only 4 people on the planet who regularly write programs on top of the RoarVM. So you would get a lot of people you can hire to help you when you find a bug. And debugging parallel virtual machines is rather tricky. Maybe David Ungar can give a hint on that, because he's been doing it for 4 or 5 years, and it probably was the hardest job he ever did. Or maybe the Klein VM debugging is harder, but I don't think so. I think the C++ RoarVM was hard. I have now, after 10 years of looking at the RoarVM code, C++ code, I'm still not confident I have all the bugs, found all the bugs that are in there.
Therefore, my question on .NET, they do multiprocessor VMs very well, as does Java, but so your Graal Squeak, that's an example of a multiprocessor capable if the image has the parallel code in it.
Yeah, I don't have any experience with Java virtual machines other than it runs on my machine, and that's where I stopped looking at it. I'm not that interested, so I can't help you.
All right, thank you.
A number of people have raised their hands.
I don't see many. So David Mason, sorry, you just happen to be the first I see.
Boris is ahead of me, but I think my question's relatively quick. So I'll just ask my question. You mentioned that you wanted to see the VM rewritten from scratch from a clean sheet of paper. What are the particular issues that you see that are problematic that stand in the way of using multi-cores efficiently?
Exactly everything that the RoarVM already addressed. So the only point is the RoarVM is the only non-meta-circular compiler. So to me, I don't want to compile C++ code to a Smalltalk processor. I want to run, so I would go from scratch by just writing the same virtual machine, except I wouldn't write it in slang anymore. I don't have to. I can write it in Smalltalk, full Smalltalk, have it compile to bytecodes, and then run the bytecodes on my hardware, and then optimize my Smalltalk versus the slang that the current Open Smalltalk compiler is written in. When Dan Ingalls wrote the meta-circular compiler, it was only partial. He wrote it from slang to C++, sorry, to C, but very standard simple C, which is highly portable. I want to have a commercial thing that lasts the next 50 years. So it must be production quality. It must be capable of completely replacing the macOS system. So I would want to have to rewrite the slang code of both the Back to the Future port, slang part, which is, I would say, 3,000, 5,000 lines of code in slang, rewrite that in Smalltalk. Now I have a full metacircular interpreter. I would then add the JIT things that Elliot Moretta added, but rewrite it in Smalltalk, not in slang. And then I would, that's my main job. Then I would add all the adaptive compilation tricks and generate hardware from the compiler, the inline compiler as well. Add all the security and tagging features that Spur and stuff make possible, but make it now in hardware. So I get the same security that the most stable computer in the history, the B5000 has, the B5000 Burroughs from 1964 by Bob Barton. So I would rewrite the VM to become stable and scalable and better than Unix or macOS. But only so I can port it much easier in the future. So that would be a job of, say, a year's work for 2 people at best. It would be highly debuggable because it would be written in Smalltalk instead of in slang. That's more work, I would guess. So it's making the step from something that already works fine and doesn't have to be fixed to making production code. And so that would be my comment on the RoarVM. That is not production code because it basically is only compiling C static interpreter into C++. That happens to not really run very well on my Smalltalk hardware. But if I want to run it on any other cloud system, like an x86 cloud system, then the RoarVM of today would be good enough already. You just need to add a good garbage collector and a few other things to make it run optimal, because that was not the aim of David Ungar's research. He didn't want to write the fastest VM in the world. He just wanted to make a parallel one. But he fixed all the problems that you can backport into the existing slang or my new right from scratch. And then it would run without any trouble and scale to millions of cores without any problems. And we've done all the work. Now we just need to make it production quality.
Okay, thanks.
Boris, he's also making compilers and hardware, as far as I know. So he's probably has an interesting.
So my real question that I am unhappy about is how come there are exactly the same things that make you not sleep at night and not make me sleep at night. They are exactly the same, and yet we never worked together, or like this is the first time that I hear about. I mean, Giselle talked about you when we were in Argentina 3 years ago. And we never, we never actually, connected together. So this is really something that we need to fix.
My office is always open. You can always call me. I'll be happy to talk to you for weeks and weeks. Everybody else who knows me, I tend to talk a lot and work together for a lot. So one short answer to it is, so Giselle is the channel you already communicated with me. So we were in communication, I just not personally, directly, but more important, look, I'm an independent researcher. So one of the things I don't need to do is publish to get grants. I don't get any money anyway from any grant office. So why publish? I only publish or share my research with interested parties, some of them in this group. Giselle publishes a little bit more, but he got stuck with his PhD, not because it was not a good PhD, but because the Brazilian government says, okay, you have to do it in 5 years instead of in 6 years. You can't be too slow. So the point is, we are publishing, we are writing, but not so often as other researchers. And basically, my thing is, most of my time is wasted on getting myself funded. That is, running an internet provider or similar things to make the money to pay for the 3 million or the 50 million mask sets. That's technical for making computer chips. So I'm perfectly happy to work with you about everything, but you have to contact us. As Mary Jepson, that I sometimes communicate with, she gives an even shorter answer. She said, instead of writing papers, I publish patents. So if you want to communicate with me, talk about my patents and you get to work with me. But the point is, we only have a small group. I have maybe 20 people working as volunteers for me, and maybe 2 or 3 on the payroll sometimes and sometimes not. But as a research group, we're no larger than 2 or 3 people most of the time of the last 20 years. But perfectly happy to work with you. I work mostly with the Cobalt and the Croquet team. That's when I really interacted with people. And then Elliot Miranda did his Open Smalltalk, and they didn't need my stuff anymore. Everybody basically only asked me one question: is when can I get my hardware? And the answer is, yesterday, if you send me $1,000, I'll send you the hardware. But the point is, most people don't want to spend $1,000 on really fast Smalltalk hardware, let alone a couple of million. But software-wise, I'd be happy to write the compiler with you, because that's the one thing that keeps me up at night. Is it adaptive enough yet? Can I skip using the RoarVM C++ implementation? Can I write it from scratch in Smalltalk? That's really where I'm stuck at the moment.
Yeah, well, this is where we have been making, well, at least some headway in the last, well, decade of trying to do this. And the point where I got stuck is, well, essentially, if the image is the squeak image, then it is inherently non-parallel. When we are saying RoarVM, right?
No, I would say the Stefan Mar worked on that. He basically found, say, 2% of the code that needed to be fixed. So then it doesn't crash anymore. You can run standard squeak. But the real point of his research was, okay, but you have to rewrite every program to actually become parallel. So it won't crash anymore after you change 2% of the code, but you still have to make a different morphic that really takes advantage of thousands of cores.
Right. Because
but that's what they did in the VPR project. So they wrote their new morphic, and it scales perfectly. They wrote the new graphics and scaled perfectly. So I would say there's not that much need for things. I would say they wrote some 30% of Squeak in a new Smalltalk version, and it scales perfectly well and has no parallel problems anymore. So combine the Frank software from the Steps project with Squeak, it's already combined. It just needs to be debugged and polished a bit. And then you have a really parallel Squeak sitting in front of you, no problem.
Well, it's more than just scalability, right? It's also scaling what you said about, well, how the software on top actually knows that it is. So it's about expressiveness as well, right? Because in any standard Smalltalk 80 image, let's say I have collect, right? And what collect is expressing is, how do I express this thing that there are objects and each of them have to be put through this, well, fmap speaking functionally. How do I represent this on top of a sequential processor? That's what the code, that's what your implementation of collect is expressing.
Mm-hmm.
Whereas, you know, you take the original Smalltalk 71 idea that each object is its own thread of execution or its own processor. Well, then you don't need any of that, right? But we have
that. You have that in the RoarVM.
Yeah, that's the project that runs on top of the RoarVM. It's called Sly.
Right.
And you just say collect, and instead of one loop doing the collect, instead it just sends a million objects, then it sends a million messages, and a million cores or virtual threads start running.
What?
No scaling need.
I know about it, and I have a problem with it because it's still representation, and we are fundamentally behind what people have been in the compiler community have been doing for the last, I don't know, 50 years, starting even with certain people at Xerox PARC. That, well, now we have ways to express things not through representation, but like when the category guys are talking about this universal expressions or universal properties, right? You can say, well, a collect, you can express collect in a universal way, right? So it doesn't matter how you represent it in the machine. So you don't care whether your processor is parallel or sequential. You're basically saying, well, here's a universal property that, well, basically you were talking about functoriality here, right? You're lifting from operating on one object. You lift the same operation to a collection of objects, and if the diagram commutes, or you even better, if such and such if such and such mapping is a natural transformation, well, then you are done. Then my code is correct, and then it is up to the compiler to actually figure out how to map that to whatever machine you're having, be it a sequential machine, then you're in a loop. If you're
we had that problem even in 1983 when we started getting the transputer. That's what I built my first supercomputers out of, the transputer from Inmos. It's a thing that actually looks very much like Silicon Squeak. So Silicon Squeak gets all the benefits from that design. But the point was, there you basically said, we have a million cores, so make a million threads, a million communications, and then that's how it's scaled. So you had to hard code that into your Occam program, and then it worked. But every time you had one broken processor, you had to recompile your program, because now you had to have one element less in your array of processors. Right. So that you don't have in the RoarVM, and you don't have it in standard Smalltalk. So, but what you still need is what Occam didn't even have. You need to write a load balancing program. Say, okay, I know that currently I want to use 10% of my cores, and they all have 1 gigabyte of memory. So let's tell these million objects to spread themselves out over 1,000 cores in memory, and these other objects all to cluster in the farming out central controller or something like that. You don't want to have it, but the point is, you now write a besides the processor process switching system, the green fed system, you write another watchdog project that just sees, hey, we have a bandwidth on one of our outbound links. Let's move half the objects to the other outbound link that's on idle right now. So I call that's an algorithm that I hope now works. I still need a name for it. So it was based on attraction and repulsion, like a magnet. So there's a tension going on. All the objects want to move outwards to all the cores, and on the other hand, there's a pull inwards, for example, by the limited bandwidth that each object needs to communicate with some central thing. You have that in Croquet, for example. So there's one force that pushes the objects back into groups, and another force that pushes them out to as many different cores. So that's my load balancing. It's just like the step in the world for morphs, that every morph gets its time. That's the preemptive multitasking, I think they call it. That makes the particles fields of a etoys or Kadama, sorry, etoys particle field or Kadama or Shadama make 10,000 objects get equal time, and then there's the next step. So that kind of scheduling, I now need to write for my random group of objects to load balance between the limited bandwidth and the limited memory access speeds of all those cores. But it's basically not related to the program. It's just a watchdog that says, oh, I see a bottleneck, let's disperse a few more. And in the RoarVM, as David Ungar left it when he had to leave IBM research, that's still manual. You just have to do that yourself. There is no code for it yet, although it's hidden by the higher level language slide. In my case, it's exposed to my load balancer. I call a load balancer a magnet thing, and that seems to work pretty fine. So I don't need to rewrite most of my code because of that. But maybe I haven't done enough benchmark yet. Maybe I'm wasting 20% of all my processing just to push these objects too often from one to the other core, and it didn't need to. Sorry, that's one warning for everyone. Even if you've got all the parallel processing, all the best compilers in the world, and all the load balancing, you still have to debug it, and that tends to be a little complicated if you have a million different threads going on. It's very easy to debug a million objects going to a million cores, but if they're all completely different and not scaled at the same, okay, then you still have a million different things to debug, and that tends to be overlooking a few of these cores. And you won't be single stepping it either, because single stepping a million times,
Right.
that's pretty slow.
Yeah.
So it's about writing the tools to let you debug a million cores, but it's doable. David and Sam Adams did a whole job in 2 or 3 years, and to me, those are mature tools. You don't build production systems with them yet. You don't build a Facebook or a Netflix out of them yet. But if you had the resources of a Netflix, you would say, okay, we'll do it in 1/100th of the time that they fixed FreeBSD. And that's how Netflix fixed their problems. They didn't fix their software, they fixed the FreeBSD kernel, and that made everything work fine. Now, in your case here, you get a couple of really good coders to rewrite the RoarVM from scratch, and now all your problems go away. You transition from a working model to a production system. And I imagine that people inside Apple did that last year or so for the M1 Ultra. They had to change everything inside, but again, we have to ask David Ungar. He's probably one of the few people in our Smalltalk community who's talked to the people at Apple who rewrote the kernel part and the core graphics part and the core whatever that Apple needed to fix for the M1 Ultra. But I don't know much about it myself. I fixed the RoarVM in just a few 100 hours, and it's good for my purposes, so I'm pretty happy with it. I just want to rewrite it to make it a nice Smalltalk program that I can debug instead of a C++ program that I hate to debug. But that's just my personal preference. I'm not claiming that David didn't write a really good program. It's just that I hate C++. That's just my personal problem. Is that answering your question? Shall we go to Milan's question, or?
Yeah,
Milan?
Okay, I have a quick note and a hopefully quick question.
Sorry, I tend to not be quick answering. Sorry.
So my note is thanks for mentioning the Ukraine effort there. It's first of all, it sounds like a practical implementation.
Could I interrupt you first?
Yes.
I just 5 minutes before this meeting started, I got a begging letter from somebody in Ukraine who cannot go to the central locations where they give food and water and clothing, because he has an Alzheimer patient sitting near Kharkov, and he basically doesn't have a car. He has no way to go to Kiev to get help. So he basically begged me for money, and I said, I'll make a public call for who wants to send this man a couple of €100 so he can survive with his old Alzheimer dad. Sorry for interrupting. Please ask your question.
Please share that communication. So that's my note. My question is, so thanks for sharing that effort. My question is rather vague, and I suspect you actually started to answer that a little bit. So it's around the massive parallel computation over distance. At some point, actually fairly soon, we start competing against the speed of light, around the world in 0.1 seconds. Is there some algorithms that sort of, automatically, define the granularity of when, the object sends the message to an object somewhere remotely, on a continent versus locally? So that's the question, so very vague, but there it is.
It is actually the heart of my research and my commercial work, quote unquote. I run an internet provider, or at least I design parts of internet providers. So on one level, I have 10 nanosecond message speeds. And so I can do a message sent to my neighbor core, and within 10 nanoseconds, I could even get my message back.
Right.
But the same message completely transparently might be going over another channel to the other side of the world. And now we're talking about 300 millisecond latency at worst. So that's, Giselle, help me, 30 nanoseconds, 300 milliseconds, that is 100,000 times slower, or 10,000 times?
Sounds like 100,000, but yeah.
So the point is, so Croquet has some experience with that. So the model of Croquet says instead of having a remote graphics terminal of a computer on the other side of the world, like Second Life had, instead we'll just send the events that change in our virtual 3D metaverse world.
Right.
So only the events, like somebody clicking a mouse, is transmitted over these low latency channels of 300 milliseconds, and almost everything else is just computed locally. But as a group, you now have 1 million people all being in the same virtual space, sharing the same video stream. So like we are doing right now. Right now, there are how many? 60, 70 video streams being passed either to a server and then compressed and sent back to each of us as one video stream, or we have 30 video streams going to 30 other people. So that's 900 different video streams happening all in parallel, but only of tiny little bits of video, not of large ones. So in that case, here we have a latency that is every time I do this, I already see that I'm almost a second lagging if I get the mirror back, basically back and forth. So how do you manage that? Now you build in the case of Teatime, you build a little model. In the case of, on one side you have a graphics card, and on the other side of the planet you have the graphics rendering. Now, some of the graphic rendering should be close by that user. So you start dividing up your channel, and some part of your channel is running at nanoseconds and others at milliseconds. So what you do is you start becoming aware of what your software is doing. And that is what my load balancer actually does. It's more looking at, oh, sorry, I'm being attacked by a night mariposa. How do you say that in English? A butterfly. But the point is, you measure, and then you plan for the low latency part to be inside of your cores and not across the planet. So you divide it up correctly. You look at your software, you simulate it, and then you measure your benchmarks. Is that an answer?
Yes, but I guess my sort of follow-up question. So is that done automatically, or is that something that needs to be, sort of programmed in? Sort of the awareness that this. Now,
my load balancer does that automatic, but it only sees the TCP, the UDP channels. It opens over Croquet to send all the events. So it's only doing it on a 1 kilobit per second message stream. So it's pretty easy to manage, even if I have 1 million of these streams. But it depends on what application. So in my case, if you would be doing a game, you would have more trouble than my Croquet model.
Right.
And for those around you who don't know what Croquet is, in this case, it's a massive virtual environment where every participant gets you play a game, you click on something, and then it says in 1 millisecond everyone will destroy this object, but please tell me if your computer is planning to do that in a millisecond. So you all have a millisecond to send them. You have 1 million participants. You send 1 packet out to 1 million people. It comes back from 1 million people, and if one of them not responding, then you can decide, okay, this event never happened, or the opposite. We'll just let that one person lag, and the other 900,999 will proceed, and this object is destroyed in the game. So it's a two-phase commit system over a millisecond period. So we call that futures. So that's a system that manages it automatically. Then I don't have to worry about the latency. In another system, my load balancer does it, and it starts moving things from the distributed side back to the local side. So sometimes you can do it automatically, sometimes you can't.
You can't, right? And I understand that in the Croquet sort of situation. Yeah, okay. Okay, yeah, thanks. That answers my question.
Yeah, sorry for the butterfly here is something like an ounce. It's really heavy, so it's like a small bird, and it doesn't like my light. But yeah, then
it attracts it. I see. Yeah.
Yeah, I forgot to close the window. I'm in the Netherlands right now, but next time when we have this, I hope to be in the Peruvian rainforest or on the island of Sambar, where we have our submarine cable, where the Smalltalk will be doing all the routing. And there, that's your other answer, I'll be doing it at 100 gigabit speed. So that is 400 nanoseconds latency for going 10,000 kilometers. Is that that's roughly it? So that's a third of the speed of light. So there I have to explicitly manage my latency.
Yes.
But it's only 300 lines of code, so it's actually much easier to debug than Croquet, which is 100,000 lines of code maybe. No, that's not true. It's probably 30,000 lines. But so it depends. It depends, but usually it's not that much of a problem actually.
Right. Okay. Thanks.
And then there was silence.
I just muted myself back.
Yeah, no more questions. Almost half of the viewers dropped off.
That's normal.
Charlie, could you type our Sambar Jitsi address in the chat? So I'm inviting anyone after this meeting is over to drop by in the next couple of weeks on our little office in the island of Sambar. That's I don't pronounce it right. It's Saint-Barthélemy. It's a French island where these people like Paul Allen, but he's died recently. But Paul Allen and Jeff Bezos and those people have their yachts, and that's where we're building a tiny little internet provider for these rich people. I heard that the director of Gazprom also has a beach there and a house and a boat. So I'm going to be there not for holidays, but putting lots of Smalltalk routers in people's homes and a few in the middle of the ocean. And we'll be happy to have long discussions on hardware, because that's one of the first places where I expect in the next 6 months to deploy a few thousand Smalltalk computers. That's our own hardware, not.
You're teasing us. That's not fair.
No, that's not teasing. You want to? I call it the Morphle power router. It's both a programmable inverter and a 12-port 10 gigabit router. And it basically just runs quick. It's a tiny little, you have a routing table. You can do that in the Linux kernel or the Unix kernel, but you can also do it in my Smalltalk. And you can program, you can make a little lab at home. You actually can already do that with Raspberry Pis. That's 100 euros. Now mine is a little bit more expensive. It's 1,000 euros, but then it runs at 120 gigabits. So that's basically one of those tools you immediately can deploy. Now, you might not know what the price for a 120 gigabit router is. We call that line speed router and switch, but basically 1,000 euros is not a bad price for that. So it's quite commercial stuff. But how many cores are on there, that depends a little bit, because right now there's a chip shortage in the market. So the Intel FPGAs that we wanted to use are out of stock probably for the next 2 years. So I have to switch to a new FPGA. And that means I don't know if it's going to have 40 cores or 60 cores on there. But those cores will probably be around 1.5 gigahertz. So 60 cores times 1.5 gigahertz. Compare that with your basic M1 processor with 2,000 million bytecodes per second. So that's 1 billion bytecodes per second. So I expect to get something like 120, maybe it will be 80 million bytecodes per second on a 1,000 euro computer. So that's 100 billion bytecodes per second. So that's roughly 50 times faster than the fastest Mac you have. For 1,000 euros. So that's not too bad. It's, however, a prototype. I don't consider that to be the computer chips that Giselle and I are making. But for that, I said I need 100,000 to make the tiny one, the 3-cent one, and 3 million to make the 28 nanometer one, which is compatible, say, with the Qualcomm Snapdragon. So basically, I'm still missing 3 million to go into mass production. But then we'll beat the shit out of the Raspberry Pi, I'll tell you. Sorry, I should not be saying shit, of course.
So it's pub, you're allowed.
Okay, yeah, let's all have a beer on my treat, but only one. I'm not a rich guy, as I already know. One of the cool things I do with my very first prototype, and it also runs on the Raspberry Pi and old Macintoshes, is write the new targeting software for the Starlight dishes. So Starlink. Elon Musk is shooting 5,000 satellites in the air that each do 20 gigabit signal to the Earth. We'll soon have 20,000 in operations. Okay. That's what one of the two things we did in Ukraine. But the point is, that's a dish that basically constantly with 2 motors tracks all these satellites and then has 100 to 1,000 antennas that are doing beam forming. So that's like running 1,000 cores on a GPU. So it's a really computational process to calculate what happens if you have 100 beams from 100 chips that doing, it's actually 25 chips times 4. But it calculates where to point the beam and then calculates which parts of the waves dampen each other out and which one reinforce itself. And then you get a malformed, skewed beam with a certain delay. And that's how you target the satellite going at, I think, 90 kilometers per second, or is it 15 kilometers per second, something like that. That shoots over you in 1 minute. It passes the whole sky, and you need to keep your beam tracking it. And that's for 100 beams, so it needs to recalculate. Again, it can't ask a data center to help it with this. So it needs to do the calculation itself. And the last 2 years, they didn't do that. So they said, you cannot move your dish. You just put it on the ground and leave it, and then it'll track the satellite. But now, after Ukraine, he switched on the roaming. So now you can put it on a 100-kilometer car, and it still allows you to track. So now it's moving a lot faster relative to each other? Can it do the calculations fast enough? It used to be 1 minute to refine the satellite and track it. Now it can do it in a fraction of a second, every second 100 times. That's more than enough to drive. But if you go in a straight line on the highway, it can now track the satellites again. But if you go on a spaghetti, no, what's the serpentine? How do you call those the roads high up in the mountain where you have to go from one side to the other all of the time with the total almost in a circle every time you go up the mountain. So the point is, then I keep losing my satellite again and again. It's not yet fast enough. So I started writing my own software to do that. And I hope that my 250 euro FPGA running Smalltalk cores, probably 40 to 60 cores, can outperform that by a factor of 20.
Yeah, meander is the word you're looking for.
Meanders, okay. Yeah, I don't know the English. In France, it's serpentine, and in
yeah,
Spanish,
well, meander refers to the very wavy river.
Yeah, it's like the river. Now, that's another place where we use. So running the software in an embedded device to track satellites is one of those things you use parallel Smalltalk for. And that's why I was very interested to hear Juan saying that he got the software analyzing satellite data inside the satellite, not on the ground, where they usually do it. Now, that is the kind of thing that Elon Musk wants to have too, because on the other side, he has a camera that tells him where the gimbal of his satellite is pointing at, so he can calibrate his gimbal is the word in English, and then correlates that with the 1,000 beams coming from the Earth, and then he knows if the Chinese have pushed his satellite out of the track or it's still in the track. So, and he needs lots of visual analysis for that as well. He doesn't just use radio pinging to get his position. He doesn't just use GPS, because some people forget that. Elon Musk, SpaceX, Starlink, they're not just for having a nice internet connection in your Tesla. They're also a military spy network that completely replaces the GPS. And the Chinese have already put a big budget on shoot them out of the sky, all 20,000 of them. And the Russians really hate them, as you might guess. Because so the point is, that's now places where the Smalltalk software really should make a difference. And I'm looking at Juan. For how much would you be willing to put quiz on such a system in a space station, in a 2 million costing 1 cubic meter satellite? They call them CubeSats.
If you want, we can schedule some other call to talk about the RISC in a bit more detail.
Sadly, Juan, I can't hire you, but I bet that Elon Musk would be very interested.
Well, yeah, I would like to understand better what you just said in order to give an opinion. I mean, you think that in order for this communication for tuning these steerable antennas to make communication effective, you need to run this kind of software on the satellites, right?
Yeah, but it's more in the line of what you already wrote. Say he has an 80 million pixel camera with 60 frames per second, getting with super high resolution. Can you analyze those?
Kind of optics?
Yeah, it's
because
optics.
you need a very good telescope to do that. You need a nice observation satellite.
So that's where the problem is. So he has all these cameras there, but basically they're just very souped up iPhones. So he doesn't have the really professional optics, because these are just CubeSats, and they have 20,000 of them. So his total budget for the optics is too small, but he does have 20 overlapping iPhone-like cameras with fixed lenses. Now that means another image algorithm to get sharp images. And
the first question to answer with such a problem is, what is the angular resolution of those cameras? You cannot do magic with image processing.
80 million pixels, I heard, and he has a
no,
wider.
By the angular resolution, I mean the GSD, the resolution in meters on the Earth. Okay, and that depends not only on the resolution of the sensor, but most importantly on the focal distance of the telescope you're using.
Yeah, okay. I would imagine, but I don't know, not privy to that data. I would imagine that he's looking for image interferometry. So basically the lenses are bad, so then he wants to have overlapping cameras to get him extra sharpness by doing interferometry in the visible and the infrared. But that's guess. I mean, that's why you need a lot of computation. So that's why I'm guessing that he's doing interferometry. But I'm more.
But then the limited function may be the signal to noise ratio of the images you capture.
That's
okay. You need very.
But the answer, Juan, I don't know. It might be that he just wants to filter out the cloud vapor, and so I really can't guess. I am only used to looking the other side, astrophysics, and there you would use interferometry, but there you don't have any clouds in the way. Yeah. So I don't know. But we can find that out for you.
That's a physics approach to it. The Russians, when they were doing the first soft landing on Venus, they did a computational approach to that. So what you do is you orbit Venus many times. Your problem is that Venus has clouds all the time over it. Yeah. So you cannot see where you're landing. Yep. And is it going to be a rock? Is it going to be, flat? Is it going to be vertical? And like, how do you land on such? Is
it a pool of lava?
Yeah. So what they did was this Professor Pytyev did this. So what he did is you keep orbiting and you keep it photographing, right? And out of 10,000 photographs, you combine them with a model of how.
So photogrammetry, just standard photogrammetry.
Yeah.
Which we also use now for making pictures of the Notre Dame by just scraping them of Facebook and other just people's iPhones and Androids. But if you have hundreds of them, you can overlap them all and then make really sharp images out of really bad piles of images. So that's just computation. It's probably quite like the software that you did give me in 2007, 8. Where you were still thinking about building the graphics algorithm. But the point is, it's quite suited to your morphic, which takes the curvature of the Earth into account, etc. So the point is, it's just a lot of computation. The point is, he needs it up in a satellite, not down on the Earth. So it needs to be a portable, single chip, 100 core thing that can cost whatever you like. It could be a fixed ASIC, but can you write it in Smalltalk? Because if you write it in C++, then it'll take you 5 years to debug it. So can you write a quick one and then throw thousands of cores at it? That's basically, I think, the solution most of these people look at, because it's hard to do computation in space, but not if you have 1,000 processors to do it with.
One I can tell quickly and for sure is that what I did was to prototype the image rectification and the 3D model of the Earth in Smalltalk, and then rewrite just 100 or 200 lines of Smalltalk code by hand into OpenCL and push that to the GPU in parallel, of course.
Right.
And that was enough to make to make a use of the capabilities of the hardware of over 90%. in
Right.
terms of memory bandwidth and,
Right.
processing power.
I
So it
don't
can be
use
done.
OpenGL. What I did,
Wow.
is I loaded the whole,
OpenCL,
yeah,
not OpenGL, OpenCL.
but that's just faster assembly. So what I did is I loaded the full 500 gigabyte OpenStreetMap, which is just a set of vectors and coordinates in my memory. I just got myself a half a terabyte of RAM. Then took RoarSal, the standard Faro RoarSal, and loaded everything as coordinates in my system. So XML to a collection of three-dimensional points in the standard points from Squeak. Had a wireframe model, added all the mesh bitmaps on all the triangles, then did a calculation. Now it took me 6 months to calculate that on a single core Mac Squeak. Then I did a parallel version on top of the RoarVM and 10,000, the ones I mentioned before, and I got it exactly in 8,000 times faster. Now that's 8,000. So if it's 6 months, then I got it in 4 hours. So I ran it 10,000 times faster in half an hour. It did exactly the same algorithm that I ran on my single Squeak for 6 months. So it scaled almost perfectly. It was completely memory bound, not bound to disk or to my algorithm. So now I knew, okay, I need to buy 1,000 FPGAs. That's 200,000 euros, and now I can run this algorithm every half hour continuously. So that is, it's the simple massively parallel. But the point was, I say the same as you say, Juan, it was only 200-300 lines of code. You write that really quickly in Squeak. Okay, the debugging, because it's so much data, it takes a little bit more time than normal, but you get it working in 3-4 days. And then you say, okay, now I have my complete map of the Earth completely updated every half hour. And in my particular case, that was my first slide. You see that in my fiber white paper. I do a spanning tree map on every point on the planet and then calculate what is the least amount of cabling to interconnect them all with fiber and electrical cable. That saves you, say, 100 to 500 euros of digging and buying extra copper. That saves on a country with 9 million houses, saves you now 50 million in pure copper that you don't need. And that pays for the 200,000 of scaling this on hardware that's off the shelf. Except I wanted to have 3 million, then I would make my ASIC, and I would have done it 1,000 times faster for the same price. But okay, that's the economics of chip making for you. But the point is, you could do that even on Raspberry Pis, and scaling is a software problem. It's not a hardware problem. That's just to make it 100 times faster for the same price. That's what hardware do for you. But it's the scaling part, in this case, from 4,000 hours of continuous calculating back to half an hour, factor of 8,000. You do that just by 8,000 times more processing power and the same 300 lines of code. Therefore, it scales. Oh, but yeah, what I actually am explaining is, but do make sure you have 500 gigabytes of memory to store all it in memory, because if it comes from disk, then you're still 1,000,000 times slower.
Amazing.
Did anyone see David Ungar or Ben Ingalls leave? Because I asked him a few questions, but
yes, and I saved the text of the chat so you can look at it later.
Okay, please do, because it normally is not saved, and I would hate not to answer those questions. Because it's their work, for those who don't know them, it's their work that my work is based on. If then David Ungar, Dan Ingalls, and Alan Kay wouldn't have done so good of a job, I would have not finish my work in the next decade. I would recommend the RoarVM. I mean, it's a brilliant piece of software. It's just a C++, which I hate.
And it's also 32-bit, so
Oh yeah, that's
I was trying to compile it on my current Linux machine, and it's easier to use an older 32-bit Linux rather than that.
Nobody has to answer this question, but could anyone tell, is it even an interesting talk, or was it actually a complete waste of everybody's time? I don't know, because I didn't see anyone's faces. I just saw my own slides and nothing else. So I just droned on without knowing if I interested anyone.
You're still sharing your screen, so for me, it only shows 4 people rather than everybody.
My screen is being shared.
Yes.
And yeah, okay, now I get
it's true. Yeah,
how do I switch it off?
Yeah, probably the same button that turned it on.
Which I couldn't find because my mouse didn't work. I'll work on it. I'll find it.
Right beside the chat.
Yeah, but again, I haven't seen the chat. No, it's a bad software. It doesn't even have a good menu. So hide video panel. No, sorry, I'll shut up.
It's at the bottom, isn't it? The share screen bit. If you maybe you've got it hidden.
Share. Stop share. That's it. Yeah. It just says share, but not share what. So now I see more faces. Okay, now I see. Anyone here in this group who want to teach 2 good programmers and 1 brilliant one about Smalltalk? Because Cesar Ayala in Mexico, and maybe Sly together with his future wife in they would definitely would be interested in a lesson from one of our experts here. I'm just an amateur in Smalltalk, so I should not be teaching them. Maybe some inspirational words on why to spend the rest of your life doing Smalltalk.
Well, it ruins your life, doesn't it? That's the problem.
That's a warning, Cesar. It ruins your life.
Okay. No, it's okay. I love Smalltalk, so, but I love it because it's the future.
Yeah, but you only seen it for 3 days, so you might find out later that you hate it. But
you won't go wrong. You won't go wrong learning it. Even if you end up using something else, you'll always think back on how it inspired you to write better software.
Yeah, it makes you better JavaScript and Python programmer just as much. It's not just a dialect you learn, it's a better way of thinking.
Yeah, I would suggest anyone wanting to know more about Smalltalk to please read Design Principles Behind Smalltalk by Dan Ingalls. It's the single most important piece of writing ever.
Sorry, could you repeat the title?
Principles, the
design principles behind Smalltalk.
Yeah, that's both a text and a video.
Pretty much, yeah, I agree.
It's to me, it's the Byte 91 magazine that got me completely hooked, and I've never left it. But I now find that tiny little bit of there's the 1.5 manual for Lisp on one page, half page, that inspired me first. Yeah. But now I rediscovered that there's one in the HOPL, the History of Programming Languages account of Alan Kay, where he has the Smalltalk variant that he gave to Dan Ingalls in 1972. That is way cooler than the Lisp one. So it's the typical understatement of Alan Kay that everybody should look at the Lisp 1.5 manual and not pointing out his own, which is way cooler and more understandable, and of course, completely written in Smalltalk. And that one is, Giselle is here for anyone who wants that particular one. But like Dan Ingalls says to everyone, if you read the half page of Lisp manual, you'll lose a month of your life. But if you look at the Alan Kay then English one in the Hopple, the history of programming language, how Smalltalk was created paper, then you don't lose half a month or a month of your life. You have the feeling like after that your brain has grown a little after you read it and said, wow, is that it? And then I need to open a bottle of champagne to cool down my brain because it's so cool. So thank you, Giselle, for reminding me that I had to go through it. We did that 2 weeks ago or something. And
certainly worth a reread. I haven't read it in ages.
yeah, so that's my inspiration. Go read it again. It's fun anyway. I also can highly recommend the other book, not Dealers of Lightning, but no, the account of how they got the Alto and Smalltalk to run at Xerox. The Mitchnick book.
They're quite good on Audible as well. They're quite nice to listen to.
Yeah, and by the way, anyone who wants all the Smalltalk books, I have 50 terabytes of stuff. Roughly 4 terabytes of that is pure Smalltalk lectures, videos, and all the books and all the scientific papers you could ever read in your life. So just send me a link, and you'll get a dump. That is, you can then organize it yourself and send me the dump back, so I can give everyone an ordered collection. But I have the raw collection. I call it the Smalltalk Museum. And for 3 years now, I'm fishing anyone who wants to organize it with me. Please do, because I get hundreds of requests for the data dump, but nobody wants to organize it. It's got cool stuff like all the lectures of Alan Kay in Squeak as eToys projects. That is 25 years of really cool stuff that never was discussed on anywhere, mailing list or forums. It's like you suddenly have Alan Kay sitting next to you for a couple of weeks. Now, and Juan actually had Alan Kay next to him for a couple of weeks. So how is that, Juan?
No, I never had Alan for a couple of weeks next to mine, shot for a couple of hours, a couple of times.
Only a couple of hours, okay.
Yeah, and it was great, of course.
Okay, yeah. Now I thought you actually were in his office for with when they were still working on Squeak in 2000.
Well, I did an internship with them, but it was remote. I only met him personally for a couple of hours.
Okay, yeah, that's a pity then. So now my whole company is remote, and everything I do is being remote. I haven't even but the point is, remote is really good, except for meeting people like Alan Kay. You actually want to be there. So it's too late. I mean, he now moved to London, so he's very close by. Actually, if we wouldn't be on this talk, I would be happily spending the rest of my life waiting in London to meet Alan Kay. But again, you only get a half a day, and that's the best you ever can do. And you would only do that if you're a PhD level student. So again, I'm missing out on all that. Everybody else around me did.
Oh.
Yeah.
Well, you know that Alan is quite active on Quora. You know.
Sadly, yes. Yeah. I want to be angry at him because you cannot copy and paste and save the Quora talk, because Quora is anti. You can't record it in any way, and soon it will be gone. But the point is, yes, I read everything he ever writes.
Yeah,
and that's what's in that data dump, of course.
I agree with what you say about Quora. That's pretty bad.
You can't even copy and paste. There's no way you can record it other than a screen dump.
I didn't try to that, and it's even worse news. But at least it's a place where you can interact with him and ask questions.
But you can also do that on Hacker News, and that's where we had ended this conversation.
Okay, cool.
But no, I have access to Alan Kay's talks and knowledge, but meeting him in person is another thing. for hours, not for a little while, that's possible, but I want to ask him some weird questions. For example, there's a famous story that Richard Feynman says on Fun to Imagine. If you Google Fun to Imagine, it's a 1 hour BBC interview. And there he tells a famous story of what happens if a fly sits at the edge of a swimming pool and then puts his feelers down and measures all the waves going in all directions and recreates a visual image of what happens in the pool. And then he makes a joke. He makes the joke of there's a girl diving in the swimming pool, and this is Richard Feynman, he says, and if she's not too pretty, then I can think about what this fly sees and how the waves go. So he makes a mental model of what happens in the swimming pool that the fly sees through electromagnetic sensors like eyes and antennas and radio. And then I realize, look, he's telling this story about the swimming pool at Alan Kay's house, the day that Douglas Adams also was there, the one who wrote the Hitchhiker's Guide. So is the girl he talks about, who's not that pretty, is that Alan Kay's wife, perhaps? She is not that particularly good. She's very nice, but she's not that pretty. But the point is, that's one of those questions you really can't ask on Quora. And I would really want to ask, did you actually sit and talk with Richard Feynman in your hot tub for hours? And is he exactly the same kind of personality that you see on the YouTube interview on BBC? I mean, that's Richard Feynman. Sorry, I'm a physicist, so
whoa,
I've seen everything Richard Feynman ever did, said, written, or done, and these guys know each other.
That Alan and Richard Feynman could have met
regularly. So, if you read the Hitchhiker's Guide of the Galaxy again from back to front, you'll notice that lots of Alan Kay is in there. There's a series of YouTube. Short before Douglas Adams dies, where you basically hear him explain. He doesn't use the words point of view, and Alan Kay's research group is not yet called the Viewpoint Research Institute, but you obviously heard that Douglas Adams has gotten a completely new point of view. That's where his humor is based on. He keeps inverting things in English, and that makes him a funny writer. That's where all his writing is based on. But I think he learned that from Alan Kay. And I want a confirmation on that. Was it Douglas Adams who wrote brilliant books, or was it Alan Kay who made him see points of view, and then he started writing brilliant books? Did Alan Kay influence or not? Now, so these are these questions you want to ask if you have more than a few hours.
Merik, theories, love it.
Merik, if you have the latest Mac operating system, you can do, I think it's called live copy or live paste.
Yeah, I was gonna say that. You can.
Yeah, you can just, it has AI built in that will do optical character recognition when you select a picture with text in it.
Yeah, but what has that to do with Alan Kay?
You said that you can't record anything or do a copy and paste from Quora. And yes, you can.
Thank you. Yes. I had there's another way of doing it. You just pull the file of the page out of the cache of Google. You go to 12feet.io or .com. That's show me a 12-feet wall and I'll give you a 14-feet ladder. That's basically things that strip paywalls of any website and therefore lets you read Quora and copy all the text. So that's an easier trick. It's just taking out of the cache of the Google search engine. So if you have the Wall Street Journal, you cannot go there because there's a paywall. But if you're the Google search engine, they just lower the paywall for you. And then that page is in the Google cache and you can pull everything out of the Google cache if you're quick enough. So you just say to Google, go re-index this website, and then you have all the pages without the firewall, the page wall. So that's a simpler trick than using optical character recognition to read web pages out of your screen dumps.
So
where do you go to?
12 feet.io, I think, but it's 12 feet that you Google. So 12 is a number and then FT. It says for
when you have the thing active, you just draw out the rectangle and then paste it somewhere, and it's reasonably accurate. So and it works with pictures.
Send me the link, please.
I don't remember the exact name of it. Do you remember the name?
No. So general question to everybody here. I had hoped that there would be one person today that said, can't we build a search engine in Smalltalk? I mean, that's embarrassingly parallel, very simple program to write. I'm talking 2,000 lines of code, but probably even a few hundred lines of code. I already have access to a complete copy of the scanned web. So why don't we make a search engine? Some that doesn't spy on you and doesn't need ads. Run it in Smalltalk, few hundred lines of code. Go do it. I'll sell it for you.
From St. Bartholomew or whatever.
Bartholomew. Could you pronounce it, Charlie? Barthélemy.
Saint-Barthélemy. Bonjour à tout le monde.
No, you're in Panama. You're not in Barthélemy right now.
Il faut bien aller quelque part où j'ai de l'internet.
Yeah, my internet provider.
I need to go somewhere I can get a good internet, and Panama actually I got a good one.
Yes, but the point is, a quick Smalltalk search engine, wouldn't that be a great thing to have? And then everybody puts a Raspberry Pi at home. We do a running on all the cores of those Raspberry Pis together. So nobody has the search engine, but together we have one. And I would happily pay $35, $40 and get another 1,000 people to buy a Raspberry Pi and stick it in their router. And now we have a search engine. It's just 400 or 500 lines of code. It's not that hard. Why don't we do that? And then I'll make some money and I'll send you all a free Smalltalk computer to run it 1,000 times faster.
Merik, there's two links. One is to a Macworld article about it, and another is to some random website.
Merci beaucoup. Okay, somebody record the chat, please.
Très bon français, Merik.
Non, je ne parlais pas français. Je sais, tu sais. Anyone who wants to hear the Ukrainian story? That's just a whole bunch of bragging and name dropping, but it is a fun story. I'm just not allowed to say it on this open channel because I'm under an NDA.
That's a good point.
But I am allowed to share it.
We're still recording. I can turn off the recording. Should I turn off the recording at this point?
No. That doesn't matter. It's it's just that I can't say it in public. This is in public, but recording it doesn't matter.
But if well, I guess Giovanni does trim the recordings a little bit, so
that's why I'm now recording as well, because I don't want them trimmed. I find these discussions, this beer in a pub, much more fun than the talk I just gave. I can have that anytime I like.
I managed to be part of that Ukraine project in a very, 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 very minor way. So that was an interesting thing.
Everybody knows about it because you saw that one day after the war in Ukraine started, actually it started in 2014, but when the Russians attacked again and came close to Kiev in 3 days, that was the moment that the vice president of Ukraine, who is also a millionaire with a startup, tweeted to Elon Musk, "Can you send me a few dishes?" And then Elon Musk sent him 120 million worth of dishes in 2 days. 2 trucks filled with them arrived in Kiev. Now that's the public note thing. 2 or 3 weeks later, the American government gave him a few hundred million. So actually he didn't give anything. But the point is, that's the public story. The more interesting story is how we got them to disconnect their entire internet fiber backbone from Russia. It was actually all of Ukraine was connected to Moscow, and Moscow was doing a DDoS attack on the full 9 terabits internet connection that went to Moscow. And then I suggested directly to the government in Ukraine to switch it to a Western thing. Except now you have a tiny little problem. How in 1 or 2 or 3 weeks do you get yourself a 25 terabits internet connection over one fiber, and which kind of switch can handle it? So I can tell that. I can also say I called Nick McCone at I called Scott Schenker, professor at Berkeley, and he called Nick McCone. 5 minutes later, he called me back and said, okay, we'll set it up. We'll send you switches. I have 2 people now working on it full time. Turned out that guy gets.
Did I tell you what happened? I called Schenker first and just gave my little spiel and said, please contact me if you have any questions, because we really like to pick your brains and get your help on this. And about 2 hours later, he called me back and saying, hey, this Merik Voswinkel guy, is he legitimate? And I went, I just got a call back from this famous Stanford professor asking about Merik. That's really weird. So it was just, you know, all I had to say was I'm calling on behalf of the Ukrainian government to get him to call me back. So it was quite interesting.
The other thing I'm allowed to say is then a couple of days later, the Intel vice president, this Nick McCone, and I and 3 others had a meeting with President Zelensky.
Oh, nice.
That was fun. Yeah, that was before everybody else saw him on YouTube channels. But the point was, he's really as nice as you think he is. He's a really cool guy. And I had not realized that vice presidents at Intel are also impressed with that kind of person. So, but I'm not allowed to say more because I'm under NDA with Intel. But Lawson isn't, so he can tell you whatever he heard, and all the others just can't come out of my mouth. But it's fun. I mean, you read about this in the paper or you see it on Twitter and you don't believe, but you can actually talk to these people. The Ukrainian government don't want to leave their bunker, but they're just 20 people with a crate of beer and a few cell phones. So they're not particularly special people, but they had a bit of a problem, of course. I mean, the Russians are literally shooting at them.
Special.
Yeah, the only thing I know for sure is that you got a chip from Intel, and after that I was out of the loop. So
yeah. So now I met the president and the vice president and also the president of Intel, and that's fun. People who look you in the eye and within the drop of a hat, within a couple of seconds, spend a few million. That is fun to see once in your life.
And so they got themselves migrated off of this backbone onto something else and preserved their means to communicate, presumably is the...
Yeah. So the satellite dishes that Elon Musk sent are just a backup, but they don't need it anymore. They now are no longer connected to Russia, and they're now connected to some European part. And 2 weeks later, the European community said, you probably can become a European country soon. I still have trouble copy and pasting the chat. Can somebody help?
You mean Quora?
No, the chat in this Zoom. My select all function doesn't seem to capture the text. Maybe there's a save chat.
Yes, there is a save chat on the...
Yeah, I sent you a copy on.
Yeah, but there's new versions add it.
The 3 dots says save chat.
Okay, thank you. I found it. Yeah. And now my computer's crashing. So that's another thing I want written in Smalltalk. I mean, we already have Croquet. Why don't we have a video channel and then do a Zoom? I mean, I've worked on Jitsi, that's written in C++, but I rather do one in Smalltalk and add it into Croquet/Cobalt/immersive turf. That will be much better. Now we don't have a video. We have everybody can share their screen, and we can still collaborate and have 500 mouse clicks on one shared screen or on everyone's shared screen. So at the same time, I could start coding on your machine while you're taking over my machine. That will be really cool. And again, 300-400 lines of code plus encrypting a video stream. Anyone know about Smalltalk doing video stream decryption? It's not encryption, expansion.
Decoding.
Decoding, yes. Anyone know about Smalltalk decoders?
Probably Craig, isn't it?
The last time I checked, Squeak only had MPEG-1.
I have written the OGL version of Google, but I haven't done the VP8 or is it VP9 now? And I tried to do the British scalable one, but the point is, if I look at FMPEG, there are hundreds of codecs and I want to have them all. I basically want to have an MPV or VLC player in Smalltalk, and because then it can scale, then I can make it fast with more cores. But the point is, nobody's written anything like that yet.
Well, there's a library you can get from the MPEG-4 people, which is license free.
Yeah, that doesn't matter. It's written half in assembly and half in C. You never port it to Smalltalk.
Yeah. Well, it's license free only for decoding, not for encoding. So it wouldn't work.
Plus, and it's not important. It's 500 million lines of code in assembly and C. Nobody's going to copy that in Smalltalk, I'll tell you.
Yeah. Well, in theory, you could use FFI to do it, but
no, you can't. There's a bottleneck. You can't do that. Which C system do you know that has 1,000 cores?
Yeah.
You would need to do reverse slang, right?
Yes, reverse slang. That's really what you need. And then you could still make it 10 times slower and it would still scale. But the point is, no, I can invent fast hardware and cheap, fast compilers, but this is a little harder. That's like I can emulate the FFmpeg on a virtual machine x86. Now, the guy who wrote the decoders system of FFmpeg is also the one who made the QEMU, which is the basis of almost all virtual machines running x86. Français Bellard. Charlie, that's the only good French programmer I know about. And he actually, François Bellard. But the point is, so he's definitely not gonna, he already made the emulation stuff to run his FFmpeg on other hardware, but that's not helpful.
He's actually Fabrice Bellard.
Oh, you're right, Fabrice Bellard. Last time it was from Paris, but I think he originated in Lyon, which is for our Frenchman here.
We've got Stuart joining us. He's a bit late to the party, but.
Yeah. Hi, Stuart. Shall I repeat my 2-hour lecture?
No, I've been listening to it. I just had to log off. I'm just double timing with some work, so I'll just put myself on mute. But a fascinating talk. Is really interesting. Thank you.
Thank you. That's humbling. I didn't think it was interesting.
It was very interesting. It was very inspiring.
It's the most inspiring talk I have heard in a long time.
Oh, no, and then
Seriously.
thank you very much. Yeah, it's my life's work, so obviously I'm interested in it, but most people tell me I'm nuts because we don't make any money here. We don't have any. We just for 14 years, Giselle and I together have advanced the state of the art a bit, and now we have to publish. Giselle, we have to publish. You have to publish. That's a joke from the best LNK talk is the Qualcomm talk. Qualcomm, is it really complex or did we make it complicated? It's about how you don't have to write 200 million lines of code to make Windows, but you can do it in 20,000 lines of code. But at the end, he talks about the other graphics guy. So we heard from Juan today, but the other one is Dan Amelang, who at that point had bought a house and got kids. And then LNK on stage in front of all of Qualcomm, of course. He says, and now finish your PhD and we'll sign it, damn it. That's the only time ever in 40 years I heard LNK swear on stage to his student, who's a PhD. I mean, he's not a student anymore, but you wrote this brilliant piece of 500 lines of code, Nile stuff, and now write it down on a PhD paper, damn it. And the same goes for Giselle and me. We need to, damn it, finish the paper.
Sorry, but did Dan ever publish his PhD?
No, he still hasn't published it. It's now 2011, so it's now 11 years later, and he's never going to publish it. He has stage fright. I don't know why. He has time enough his money enough to write it. He just doesn't want to publish. So it's a stage fright. I don't know. Giselle doesn't have that problem, but I have a similar problem. I don't think it's good enough. It's not publishable yet. It's everybody asks me, where's the hardware? Yeah, at the moment I have a $23 million wafer scale in front of me. That's the moment it's easy to publish. But my aunt would ask me, my mother has died, my aunt would ask me, Merik, it's all fantasy. Where's the thing? Show it. Now, yeah, you can buy $1,000 FPGAs. We have 2 ASICs now. We're gonna. We did a chip. You know, shall I tell what happened with it, Giselle?
Do you want me to show it?
Yeah, show it. So we did a chip 2 years ago, and the fucking FedEx lost it in transit.
No.
So our first chip is out there somewhere. That's 9,000 euros and 4 months of work completely lost. Thank you, FedEx.
Oh man, that sucks.
Oh, well, yeah.
But I have a whole bunch of FPGAs if you're interested. I mean, we do have hardware, lots of hardware. It's just not very cheap. $1,000. The cheapest hardware I have was $200 Zinc processor on an FPGA, the parallel board. But the point is, we have lots of hardware, but it's
just
not...
to be clear, this is not a silicone squeak chip.
No, it's an FPGA.
Yeah, but it's
so it's a prototype.
Not. Yeah, but it's not.
Can you guys see something? Can you guys see it?
Yeah.
No, you're not sharing your screen yet.
Yes, he is.
Oh yeah, I see it.
I can see it.
Yeah, sorry. So that's the real chip. You want to see? This is a 130 nanometer chip. So that's 130 nanometer.
Skype is being really weird for me. It says that there's one participant, but so.
It's not Skype. This is Zoom. So
Zoom, yeah,
I see
Zoom.
it. Who else sees it?
I see it.
I can see it. Yeah.
Okay, so the
everybody
bottom
sees
part,
it. So
okay,
I
so
see
the bottom part. Let me zoom in to the.
So
bottom.
let me tell you, for the people who don't know how chips work, a chip is nothing more than a drawing. We just draw the transistors in very specific sizes, and he's now zooming into it. So what you're seeing is the effect of millions of these tiny drawings on top of each other. So he's now zooming in, and now you get to see grayed out areas, and soon we'll get to see individual transistors. Why don't you go first to the individual transistors, and then we zoom out?
Yourself?
Yeah, but first I wanted to say that
So-
this part here, the bottom part is the part that was designed by a company called eFabless.
Yeah, so they're the
our
CAD
design-
software guys.
Yeah, so our design is the top part of the chip. So for everybody that participated in this Google shuttle, Google financed it.
Could I interrupt you, Giselle? Juan, every time I do this, I picture your software rendering this, not this shitty piece of Linux garbage that was written in 1991. So picture this as your software, 500 lines of squeak rendering or quiz rendering code. Go ahead, Giselle.
Case layout isn't that bad.
Zoom in, please. Zoom in. I want to see a transistor.
So let me just explain.
First, zoom in, Giselle. Please.
No. Let me just explain. So this bottom part.
It's going to take
has-
hours. Zoom into the transistor, please.
No, it doesn't take hours. For example, here at the left, there are 2 memory blocks. So let me zoom in.
So it's many layers. So we can switch off layers, and then you see what's underneath the
Yeah,
green,
so-
and then there's this. Now you see transistors,
That's
but
what
they're
memory
still.
looks like. That's what memory looks like. But normally the metal. So this is 2 kilobytes. I forget how many kilobytes it is. It's a very tiny memory, but it's not very efficient. And you have 2 blocks of these.
Yeah, he says memory, but we think caches. These are caches for
No, they're
microprocessors.
they're normal memories. They're not caches. And there's this big rectangle is another memory that's even less efficient. So they were afraid that the memories on the left would not work because this is all experimental design. So it might work or it might not work. And so this is, I'm zooming in here. This is a memory, another memory. I'm going to zoom out now. And so this bottom part has a RISC-V 32-bit processor. So that allows the software, so it connects to some pins, so you can connect it to, for example, an FPGA like the ones that we use, and then you can test the rest of the chip. So let me zoom out completely.
I would still rather you zoom in and show us one transistor. We still haven't seen one.
Yeah, I'm going to show it. So this region
So
in the
this
middle.
zooming in is 1 billion times. If you zoom out, you're 1 billion times less than if you zoom in. It's nanometers that we're looking at.
Okay, so here we have a matrix.
A microscope only zooms in 1 million times at best, and most optical microscopes only 1,000 times. So zooming in 1 billion times, you can only do that with an electron microscope.
Yeah, so this is our design, which is a matrix of 16 by 16 little blocks. So I'm going to zoom into one particular block here. They're all identical, so it doesn't really matter. So this is our asynchronous programmable block. So this block can be configured.
I called it in the talk the Morphle Logic, but it's asynchronous logic based on the path programmable logic method. So it's
so each one you can see that it's connected to the guy on the left, to the guy on the right, to the guy on the top and the bottom. They also
and it's covered by another layer. So we're looking through one layer into what's beneath the layers. So the red is beneath the layers, and the green is above the layers.
Yeah, I can turn on and off any layer so that we can only look at parts. But it's a little bit empty. You can see sort of.
Zoom in further. Let us see one transistor. We're still looking at 1,000 transistors.
Yeah. So any of these things here. So these are wires. So these are little. Let me select something like this. So this is a connection, and these are transistors. So I'd have to turn off most of the layer. Let me turn.
So the point is, a transistor is just a rectangle. That's the gate or the drain, and then there's a huge metal bar next to it. That's the wire connecting it. So the transistors are actually tiny wires, and the metal wires they're like football fields in comparison.
So I'm turning on the layers.
So now there's no layers invisible, but you can scroll a little bit down and you see the layers.
Yeah, so yeah, these layers.
Now you have here's 1/3 of the transistor.
Yeah. So
it's let's say the drain or the source, and now overlaying in the other direction is.
Yeah, it's too bad that it uses numbers for the layers rather than the names. So I don't really know what I'm doing here. What layers, turning them on and off.
And the file we're looking at is something like 300 megabytes of just blocks.
Yeah, so these are basically the transistors, these H-shaped things here when they cross with the. So
they don't cover completely; they cover partially to get a partial semi-conducting.
Yeah, so just this central region here has we call them positive or P transistors. So we have 8 of them, and we also have 8 of the negative or N transistors. So because we have both P and N, we say that they're complementary. That's why it's called CMOS, complementary metal oxide silicon. And if I zoom out, so now that we're only seeing the transistors and not the wires, you can get an idea of how many transistors. We have about 300 transistors in our basic cell. And then you have...
you compare that with 1,000 on an FPGA. So these are...
Yeah, so we have 256 of these, but you can see that we actually had space for a lot more, but we ran out of time to... unfortunately, if you...
We ran out of time to debug the shitty Unix software that they've been using for 25 years, but it's so buggy.
The problem we had is if we use a design that had twice as many transistors, it would take 100 times longer to route. So it was not linear. So we were able to do this design okay. Then we doubled the number of cells, and then suddenly it took 5 days for each attempt to route. So we ended up.
And that's where parallel processing guy said, let's write the whole thing in 400 lines of Smalltalk and run it 1,000,000 times faster. Why are we fucking around with this 25-year-old bad C code that nobody understands? And so.
Sorry to interrupt, folks. I take it just a minute. I need to run now. I will need to leave the meeting.
Right.
Thank you very much, Merik and Giselle. You know, I am a long time admirer of your work since we first met maybe 15 years ago or something.
I met Giselle because Juan told me, go meet Giselle.
Yeah,
So
I
thank you very
remember
much.
that. Yes, I thought, well, these two guys should meet. They are extremely alike, way more than they are like me at all.
You know the story that they're intertwinkled, Alan Kay and his wife thanking Ted Nelson because they met, because Ted Nelson said, you need to meet this girl and you meet this Alan Kay, and they married, and they're now 40 years later say the marriage turned out better than the movie we wanted to work on together. But Juan, you made the marriage between Giselle and me, except we are not married, but we have been working for at least 6,000, 8,000 hours nonstop together, if not more.
Thank you so
Thanks
much
to you,
for
Juan.
remembering. Yeah, I'm very glad of being of a little help there.
Yeah.
Keep the great work, and if you want to talk with me about any of these things, about satellite technology or whatever, just drop me an email and we schedule another
Charlie, so we're waiting for money, and then you get a big job from us. As I promised in 2008.
No, but let's talk interesting stuff. There's no need to talk about uninteresting stuff like money at all.
Right.
Well, thank you very much, and let's keep in touch.
Yes, please.
Good night.
Good night. Let me just share a part of the Silicon Squeak 5 slides, which show where the Morphle Logic fits in the process. If you want that, I can do that. Now this is going to be a little bit harder. Let's see.
Because his computer is slow and the software is really, really shitty.
No, it's because it's a presentation. So let's see if I can share a window instead of a screen. If you guys can see the presentation.
There it is.
Yeah,
it works
that's great.
perfectly fine.
Okay.
Sharp and fast. Go ahead.
Yeah. So this is. I'm going to skip it. This presentation is of walls and walls of text. So I'm just going to show 2 or 3 pictures of it. This is the motivation. So currently you take some C program, you compile it to x86 code. This is how you do it. Somewhere in the middle, you have the intermediate code, which is
syntax tree.
Yeah, so it has a control graph where each node of the control graph has a data flow graph. And then this gets crunched down into x86 binary. And then here's a Zen 2 processor, and it will extract the control flow for the branch prediction circuit. And then it will also extract the data flow graph and put it in their schedulers here. So I thought, well, what if I open up this processor so that the compiler can put the control graph and the data graph directly into the backend? Why go through this indirect method of generating this x86 binary and then expanding it back into the data structures that the compiler had it in the first place? So this is sort of what this is about. So I'm going to skip. So this is the overall architecture. These yellow blocks are memory, about 32 kilobytes of memory each. So I call them the external flow processors that they connect to the network on a chip. Then we have the control flow processors. They handle the control flow graph. And then we have the data flow processors. They're 8 bits each. They are ALUs. And then we have the Morphle Logic, which is the chip that I just showed. So
those chips we just saw, they cost 3 cents if you would make them.
Yeah. So you saw a 16 by 16. You can imagine that we have a larger C here of things, but we also have these.
Sorry, that's from Alan Kay's Sea of Gates, an ocean of gates. So many that you could do anything with them. It's like throwing a bucket of water in the sea, and there's enough there.
Yeah, so there are 5 kinds of instructions. So I've coded them. So the control flow instructions are this bluish. The memory instructions are yellowish. There's the configure route in the data flow. I'm going to just show one detail. So what happens is the configure instructions, you pass it 2 numbers. One is just how many ALUs you need to process your numbers. And the other one is if you want a vector of them. We'll see them in action. But you can also configure a Morphle Logic block. So programming the Morphle Logic block is a basic instruction of our processor. And that's what the next slide shows. So this is what Morphle Logic, each of those 256 blocks can be programmed in one of 8 configurations. There are actually, some configurations are the same except rotated 90 degrees. So the in is the same thing as a 0, but rotated 90 degrees. The horizontal connection is the same as the vertical, and the 1 is the same as the Y. So here's an example of something that's not very efficient to do in Morphle Logic, which is a full adder, ripple adder. So in green, you can see what an exclusive OR gate looks like. It takes 6 Morphle Logic cells. And the purple ones are other exclusive ORs, and then There's an AND gate also. So you put it in 3-bit numbers, 2 3-bit numbers, and you get a 3-bit result. But so this is not something that you want to do because the Silicon Squeak 5 already has adders, so you don't want to waste your Morphle Logic in that, but it just shows that you can. So anytime you need some special logic, you can just insert an instruction in the middle of the other instructions in a matter of nanoseconds, or at most a microsecond. Wham, the hardware, the logic block will be ready to execute. Now, like I said, it has adders. So for example, if a configure instruction is 3-1, then it will connect 3 8-bit ALUs, and then every instruction you give it, plus, minus, multiply, whatever, will take in 2 24-bit numbers and will spit out a 24-bit result. I should have put output arrows as well, but you get the idea. Or you can configure 1-5. That means that I want 8-bit numbers, but I want 5 of them as a vector. So that's how you allocate. And or 3-5, that will allocate 15 ALUs, 5 blocks of 3 each. So every instruction that you give, so you say add, you're going to add 5 24-bit numbers. So just if I come back to here, oops, sorry. So that configure 5 would the first one, the configure 3, would take these 3 blocks here. Oh, my cursor isn't showing, right?
It is. It is.
Yes, we see
Oh,
it. I keep track that everything goes fine. Just don't worry about it.
Yeah. So the first configure instruction would take these blocks, and then all the instructions that follow would operate on them. Or the second one would take these 5 blocks. And then the third one, you'd need to have 15 of these slices free. So the idea is that even a reasonably small Silicon Squeak 5 would have about 256 of these slices. So
and therefore capable of running a 128-core x86 emulation if it wanted.
Yeah, exactly. So here's the memory instructions.
So a $20 high-end x86 Xeon or AMD that's cost $8,000 will be outperformed by a $20 to $40 ASIC.
Yeah, we'll see when we have some benchmarks. But so the assembly instructions, the memory instructions, you start with reads and you end with writes. And you can configure the memory blocks as well. Like I said, you had those bunch of little yellow blocks, 32 kilobytes. You can split them up in interesting ways. And for example, a piece can be your stack, while another piece is your object, yourself, the receiver of the message, and so on. So I'm going to skip over that. A key thing is that each instruction has a number of inputs that are at the top and a number of outputs at the bottom. So here are the instructions that have been defined so far for the data flow. For example, the multiplication, here I explained them a little bit. So the multiplication actually generates 2 results, high and low in the division, remainder in the quotient. So what happens is, I'm going to go to an example here. There's these route instructions that will take a bunch of inputs and reorganize them. And you cannot actually connect them to, and here are the jumps. I'm not going to go into too many details. I just want to show an actual example. Okay, so here's a little program in C that goes through a tree and finds
that syntax tree.
No, sorry. No, it goes to a C tree. So each node is this tree node, Tn, that has an integer k, and then it has a left and a right pointer. So this is a pointer tree. Actually, pointer chasing is the worst thing for our processor. So this is, let's say, this is what our processor is really bad at. Okay, but yeah, so it's an example. So memory 1 is the local registers. Memory 2 is the heap. And the configuration 0, you can have several configurations. So, but we only use one in this example, which uses 2 ALUs. So that means that we operate on 16-bit numbers. And I define a few constants here. So here's search, and it will read P from memory 1. And then, depending on whether it's 0 or not, it will return. And if it doesn't return, then it will jump to the next block, which is this one here, which will read 1 from P, 1 from, P from memory 1, key from memory 1. And then it will use the P that it read as an index in memory 2. So these are switching because normally you don't need these routing instructions. Normally the data flow instructions fit together very efficiently. In this program they don't. But you can see that I compare if the two values are equal, and I also compare if they're greater at the same time. You don't have to do sequential. And then depending on the result, if they're equal,
well, one of the good uses for that is to have tagged objects memories. So
yeah. So if it's greater, it goes to the then label, and if it's neither 0 nor greater then if it's less then it goes to the next block, which is this one here, which will just read P left pointer and update P with it, and then we'll jump back to search, or the then block that does the same thing except that it goes to the right. It follows the pointer. So yeah, like I said, following pointers is really bad. So I have an alternative textual syntax. So this is what the textual syntax. I can't understand this very well myself. So the main syntax for our assembler is these little colorful blocks. So this is what you see on the screen when you program in assembler. And here's the machine.
Graphical assembly language.
Yeah, so you can type the text if you want, but I find it very unreadable compared to the graphical one. And the machine language for this only takes up 45 bytes, so it's very efficient compared to normal processor. And here's the machine language. It actually has only 4 blocks. The program counter can only point to a block. So you can only point to either the first line here, or the second line, or the third, or the fourth, and jump back and forth between them. You can't, the processor doesn't deal with the instructions in the middle of a block. Unlike most processors, there are other processors. There's the mill.
In assembly language, a block is everything that happens, including loops, until you jump, and then the block stops. So that's another subroutine.
Now, for this processor supposes that our inlining compiler can take a bunch of loops and group them together into bigger blocks, because otherwise, if you just have send messages, it won't do such a good job. So it depends on the adaptive compiler being able to extract. This is not a very, like I said, it's not a very good example. But yeah, so the idea was just to give a flavor of what the current Silicon Squeak looks like, because the slides that Merik had shown were from 2010 and 2012, which was And for those designs, the idea was to have it use as few transistors as possible, so that given area, we could have as many silicon squeaks as possible. Now, each silicon squeak would not execute very fast. So we were worried about byte codes per second per joule.
Joule is energy.
Energy, yeah.
Petajoule, pentajoule. So
yeah, so we were our previous designs were favorable relatively, but in terms of absolute performance, any Zen 2 or whatever blew it out of the water. So the idea with Silicon Squeak 5 is to not only have the single thread execute, so you can allocate many ARUs to get the job done, but also we can have other front ends beyond the Squeak bytecode. So we can use something like QEMU to execute ARM or x86 or RISC-V.
Which is just a concession to selling extra chips and selling it to data centers. Not a concession to doing better work. It just says, okay, we'll waste half the chip on just appeasing the stupid managers who don't.
Well, what happened? Yeah, what happened was that I came up with an idea of that we could have all the nice features of Silicon Squeak as an extension for RISC-V, which is why I joined the J extension group, because maybe they weren't thinking along the same way. They went in a different direction, but that was the idea. So I came up with.
Can I ask you a question?
Yes.
Yes.
So
that's
how
why we're here.
How do you express the organizational layer of this? Like up to this point, you've shown I guess that's the Sky 180, right? So that's the implementation layer, right? And then you've shown the architectural layer, which is what the instruction set of the processor looks like. Yes. But how do we express how this is actually, between the architecture and the implementation? There's this whole organizational layer, right?
Yes.
So you would need something to how, between the gates and the architecture. How do we express, like, what is it in Smalltalk? Is it in some kind of traditional?
So for the other listeners, note his shirt. He's a RISC-V designer. He's another chip designer, Boris. So
no, sorry, but I don't quite understand. Do you mean if I'm doing
Verilog? He's talking about Verilog, or
Well, what do you use for that? Like for what usually people use either Verilog or VHDL. What do you use?
Yeah, so I'm using Verilog right now just to get something done, but I have in the past used a Smalltalk-based ChipCAD system, very interesting one, that runs on VisualWorks called
IDAHS.
So I didn't like that, but it was a proof of concept. I mean, if the guy wrote that, I could write one. But so it's on the to-do list to do everything that you're seeing in Smalltalk. The simulator for this is in Smalltalk.
Now, let me interrupt again. So everybody knows about the meta circular compiler. You write a program, and then it compiles into its own compiler, virtual machine, bytecodes. You write it in itself. Now, Giselle just said we can do the hardware meta circular compiler as well. We write it in Smalltalk, and it generates new microprocessors automatically.
Yeah.
Not new for you, but I interpret it for the rest of us.
Yeah, I've been thinking about this and playing with the little prototypes for about 15 years now.
Yeah, but Boris, if you
get it into a point where it actually works, and now, about 3 or 4 years ago, I saw this thing, this people do this NMyGen thing where you don't need, and this is an important part about education and about how to get an actual, people starting to want to learn this stuff. you know,
Yes.
that there is that open source and the whole thing is about this vertical integration. And now there are these guys that you can write a chip without learning Verilog or VHDL or anything. You just need Python, and you're good for, you know, or there's a bug in your microprocessor, and you don't want to go the inverse vandalizing things, as Alan Kay would say, you know, making workarounds because there's a bug in the processor. You just go and fix it in the same Python that you write your, you know, application, compiler, operating system, and everything.
Saving yourself 10,000 man years.
Really beat me to it. I've, you know, it's just, you know, the day only has 24 hours, and I do, you know, there's a bunch of other.
Boris, I was an outsider, and I was amazed when I learned. Look, the reason compiling software into a piece of hardware doesn't usually work high-level synthesis is because they target an FPGA. But if you target Morphle Logic, that is suited to be defined hardware blocks into. So if you can, instead of targeting what is out there, you target what you made as useful to target. That is, Morphle Logic is made for software to generate and auto route and map at that low level, then suddenly it becomes really simple. So pick your language is the answer, not pick the EDA or GDS that you want to output, or pick the FPGA, which is a very limited paradigm. So use the right language in the first place, and then it turns out to almost roll out of the principle. And that, to me, was the eye-opener. That's made me into a chip designer that I actually wasn't when I met.
Let me just mention that these Python packages like myHDL or mygem or
Blue Chip, System Verilog,
they allow you to create a program that when it runs, it will generate a chip. It doesn't allow you to take a random Python program and convert that into
of course. Yeah, I understand that.
No, because there are a lot of people working on that. That's called high-level synthesis.
Yeah, that's HDL. Yeah, that's but mygen and nmygen, they don't do that.
It's like the chisel, the chisel that people.
Yeah, but they're just combiners of library blocks.
Yeah. So, or for example,
well, it's elaboration. It's all it's doing is elaborate.
Yeah.
Yeah, but my point is that. So there are these two lines. One is using a nice language that when you run your program, it generates a circuit. It basically says your program says, oh, add a register here. Oh, do this or do that. It doesn't.
Right.
Normal. So it's the same thing that the MIT people did with BlueSpec. They took Haskell.
Yes.
Converted it. Then the Chisel people at Berkeley, what's Scala? So
over Scala, yeah.
Spinal HDL is another Scala package as well. So
I hate them all.
But what I'm saying is that all these packages, they are a library for the language. So you write a program in that language that calls the library, the Chisel library or the Spinal HDL or mygem or whatever.
I would call them Lego blocks.
But there are a lot of other people.
But look, how is that different from what people call embedded languages? Right. That's language embedding, right?
Sure. Yes. I agree. It converts.
Like in Lisp, right? There are a lot of languages embedded in Lisp, like ACL2 prover is embedded in Lisp, for example.
Yes, you're exactly right. In fact, for example, when I created a CMOS simulator in Self, that's exactly what I did. I extended Self. So there's this library. When you import it, Self is suddenly a hardware modulation language. There is the thesis of a friend of mine was called Self HDL, where he actually had a graphical thing where you could connect. And the idea was he he never got to the key aspect of his PhD, so he finished the project. It was not complete. He wanted to modify the self-scheduler such that you could have your system, this part to be hardware, this part to be self-objects, and you would never know because they're exchanging messages. So the Morphle Logic idea is sort of like that. So I just showed a little Morphle Logic block, but if you have Morphle Logic blocks, if you have a big circuit where the Morphle Logic blocks are far apart, you don't pull a wire all the way from here to here. You can, but normally you don't do that. You convert your signals into a message, goes over the network on a chip, and arrives on the other side. So on the other side, it might be software.
So now you can suddenly address millions of blocks. Don't have to attach them yourself.
Yeah. So the idea is that all connections, long distance connections between Morphle Logic blocks are via messages the same as the software uses. So at any moment you can replace a software block, a piece of software with the equivalent hardware or vice versa, and you never know because the messages continue to do the same job. So this actually I had already been working on this idea, but that
now we have a hardware object. You have a real hardware object, and it just looks like a software object. You don't literally don't know the difference.
Or to the hardware, your software object might look like a hardware object.
Yes. So you can now prototype your hardware by writing software objects and then replace them with hardware objects later.
Right. So now I have another
change your design.
So this Morphle Logic thing, is that specific? Like we were talking about the Morphle Logic, and we were talking about the wafer level integration. Are these connected things, or are they?
There's not one Morphle Logic. I did 2. Giselle did 3. So we have already 6 Morphle Logics.
But you saw that using that old 130 nanometer process, just 256 cells took up a little bit of the block. Well, actually, if we redesign it at the transistor level, we can probably get it to less than 1/10 of the size. So you'd be able to get 2000 in that area, but that's not much. So if you have a wafer scale, the advantage is that then you really don't have limits.
I said we have 45 trillion transistors. Now divide that, so I could have
divided by 300.
1/100th of that, so that's half a trillion to a quarter of a trillion of these logic blocks, which is staggering. I mean, that's a million times more than an FPGA.
Yeah, so the wafer scale only buys you really, really large things. So because but you can't put them on a chip. I mean, even our cheapest chips that we plan to design will have a little Morphle Logic block, but not very large. So
now we're talking cents per chip, and it still can have Morphle Logic, except no longer thousands and thousands.
But the problem is that now if you put 2 of these chips on the same board, then they have a very weak connection between them. I mean, even compared if they're in the wafer, then you have the top level wire.
Well, how weak? I mean, you
like this one, eh? So this one is a
no weaker than your connection to memory.
No, yeah. What I mean is, if you have 2 chips on the board, first of all, you only have a few pins. You can't have.
I understand. No, but Giselle, fundamentally, you've got to have some connection to memory. You cannot do everything unless we're talking
the
about
memory is SRAM in the chip.
Memory. Oh, okay.
This chip, for example, has 256 kilobytes of memory inside, but it can only do 340 megahertz wiggling, bit banging its pins with the PO. This is a Raspberry Pi 2040, a 17-cent chip. But the point is, it's really weak at I/O it's really fast with its internal memory, but that's limited only to 1/4 of a megabyte. So there's trade-offs. The trade-off is it cannot even do a gigabit of talking to outside connection. It can't run a hard disk. It cannot run an Ethernet, but it can run really cheap connections with a tiny. So Morphle Logic is like that. So these are POs from the Raspberry Pi 2040, and a Morphle Logic block is a really good PO. It's even better than this actually. It's more adaptable, etc. But the point is, so it has its advantages and sometimes it has disadvantages. If you would want to use the same thing with external DRAM, you suddenly would need hundreds and hundreds of Morphle Logic blocks just to talk to DRAM.
Yeah.
But the fact it's asynchronous means okay, but it does run at DDR4 speeds. But it's just a waste of transistors now.
Yeah, for the Silicon Squeak 5 design, so the previous Silicon Squeaks, they each processor had about 20 kilobytes of cache in it, and then would connect to some external DRAM controller or something like that. For Silicon Squeak 5,
with a 20 gigabit link, yeah, so that's fast.
Yeah, but for Silicon Squeak 5, basically every ALU is surrounded by 4 of those little yellow blocks with about 32 kilobytes each. So you can still talk to blocks that are not your immediate neighbors. It's just that it's way faster. And the idea is that you really don't need much memory because you're only going to have a few objects in your memory. The other objects are going to live in the other memory, and the other memory, and the other memory. So
so it's a huge cache distributed over a huge number of tiny cores.
And if you have, for example, a huge array, if you have an array that's 20 megabytes, you have to break it into pieces, and then each processor gets a little piece. So when you send a message, all the processors operate on their little the concurrent aggregate.
But all those tiny little blocks, if you wanted to sort them, that would be done by basically copying every block at the same time because they're all tiny little blocks. So they really rewriting the entire memory in a different order would take only 20 instructions, 20 cycles instead of it's a 20 megabit. That could in a normal processor cost you 20 million cycles. So some things go really fast.
Okay. Well, now what does a Smalltalk 80 image, like a Squeak image, look like in such a distributed memory?
The hardware would be able to read and write and allocate and garbage collect the memory blocks while also encrypting and decrypting at line speed. And so basically what we call the object memory manager in Squeak would now be completely in hardware. And therefore 2 nanoseconds for a whole, create a new object, duplicate a new object, garbage collect, move it around the memory. It could be really fast. Giselle doesn't like that part. I like that part.
Are you saying this works now?
Yeah. It was demonstrated in '86. So yeah.
Yeah. So Merik talked a lot about David Ungar's RoarVM. There was this PCI board that had what's called a Tilera chip, which had 60.
I had one.
But that worked at 50 nanosecond speed for a whole object. In the what's the name? It's the guy who did the object hardware processor in 5 blocks in '86. It's in your slides and not in my slides, so.
No, it's in yours. You showed the Bill Daly's.
No, the other one, not Bill Daly. The weirdo from, I think it was Norway or so in the '80s, who had a company just doing object hardware stores in 5 different chips in '85.
You're thinking about the recursive from.
Yeah, the recursive.
Yeah, but that wasn't very parallel. That was a very sequential machine. So
it was very sequential, but it had hardware blocks. But the point is, there's modern stuff that does that too. So from my point of view, is I find the fact that he needs to do 5 or 6 or 8 memory writes just to create an empty block, empty object, that slows down my Squeak a lot. If I allocate 500 gigabytes of array, it takes now a minute in Squeak, and with my hardware blocks, it would create the whole thing in 50 cycles.
Yeah, the big difference is that the Tilera actually has the caches, so the RoarVM deals with that. In our case, we're talking about memory blocks that are software controlled. So your software divides it. So you have to explicitly copy objects between the memory rather than depending on the caches. But that's the main difference. In theory, if the RoarVM can work on the Tilera chip, it work on this architecture as well. And the big deal was, for example, Morphic has a lock so that you can only have one thread running it. So you have to rewrite some parts if you want to have the advantage.
Which was done, that's done by the Frank project. So they rewrite Morphic completely from scratch to be vector oriented and completely massively parallel.
Yeah. So, but the Squeak as is, I mean, imagine that you load an image that you already have somewhere, then it's going to suffer a bit, but not because of the distributed memory. It's just because if you look at all the processors, you're going to have 2 processors doing their job. Then this one stops, then this one starts, and then this one stops and it jumps here. But always 2 processors rather than hundreds of processors doing stuff. So because Squeak wasn't written to take advantage of that, but
right. This is like how to get around the fact that the Squeak image just insists on, well, basically expressing its serialness, like the serialness of the processor. And I'm not even talking about.
I would say not the Squeak image; it's just the Squeak Morphic part.
Now, something that's really important that when I first gave this talk about Silicon Squeak, in the audience was one of Alan Kay's students, Alexander Warth, and he wasn't understanding. He says, you say that you have all these separate memories, but Smalltalk has just one memory. And I said, no, it has one address space. Every object has its own memory. There's no way, there's no sequence of byte codes that will allow you to read a byte from another object. You can only read from
No, that's fine. That's fine.
Yeah, but he hadn't understood that. He thought of it like in C program where a pointer can.
Yeah, where it's just.
Where that's 4 gigabyte.
Yeah. No, that obviously, yeah, you have a fixed organization of what your object graph looks like. Right. Well, you have an object graph, and that is your memory model.
But what I mean is that with that memory model, we can split objects among 1,032 kilobyte memories, whereas you can't do that.
Which is what RoarVM does.
Yeah, but you can only do that if you have this model where no objects can touch any other object's memory, because otherwise you can't put them on different memories. Because then this guy might have a pointer to this guy, but it has a reference to that guy. A pointer is one thing, a reference is another thing. It has a reference.
Yes.
Then we look up in the object table, and then we find out that it's in core 95, and then the message goes through the network. So that all handles. So that's the reason why we can do this in Smalltalk and can't do it in most other languages. So
that's what I missed in my talk, telling everybody massive parallelism is easy in Smalltalk. It's fucking hard in any other language. That I mean, I don't want to force everyone to use Smalltalk. It's the better language. It proves in reality.
Now, when Silicon,
I quit the language programmation when I was programming microprocessor, and when I heard Quick is the only language can work on all the machine of the world, Mac, Linux, PC, microcontroller. So why don't we use that language?
I will tell you later, it's in all LNK's talks, because this world is run by stupid people and managers who don't want to think. That's why. It's animal behavior. It's not has to do with rational thought. It's pop culture. It's not. If they were all scientists, these managers, we would have all those things. But you don't have them because they don't want to think. That's managers only want to do what I learned when I was 5 years old, and I don't want to think about it. So that's the short version of it. It's more complicated.
In 96, when I get my exam in computer science industrial things, they never taught me about that.
Yeah.
That's crazy. It's a universal language.
The world decisions are made by average people. If they were not average people, they would be programmers like us. Except that the problem, your question should be asked, but why don't we make decisions on how a computer is built and how what processors used and in what language you write? Why does your boss make it? Your boss doesn't know anything. You know something. That's why he hired you. But that's the other problem. Most programmers are bad because they're hired by managers. I'm more than average programmer, so no manager will ever hire me. They always tell me, Merik, you're way too clever. I don't want that in my team. You might overrule me. You might tell everyone else that I'm stupid. So he feels threatened in his macho behavior. So he'll only hire people stupider than he is. And that's why the whole company is stupid.
Yes, I don't work for no company.
No, but that's why I work with you. So but that's the exception to the rule. You're the exception to the rule, Charlie, but the manager is not, and that's why they use C, because they just hear that on the golf course that every thing must
the only book I had in this period is the Cunningham and Ritchie, the Black Book.
Yeah.
They didn't talk me about the Smalltalk.
In the past, they said nobody's ever fired for buying IBM. What they didn't tell you is IBM was the worst hardware, the worst software, it was most expensive, and it never worked. Yeah, but that doesn't. That's not.
That's why no more IBM. IBM is dead.
Yeah, so it had to die. It was done by stupid people who didn't know how to program and build computers. They just had money and customers and nothing else. So they got the worst of the worst of the worst. It still took them 50 years to die.
My one interaction with IBM, they were going to hire me to do, someone had written a set of drivers to test all their new hardware. And he had written this monolithic thing in C and was finding it harder and harder to maintain. And he wanted me to maintain it. And I looked at him for a while and I said, look, I'm not that great a C programmer. I'll run into the same problem you do. So instead, what we should do is use something like Visual Basic to create a graphical framework that calls your stuff. And any new driver you add is written with the framework in mind. And he goes, no, we can't use BASIC. And I said, why not? Because BASIC is too slow. I didn't take the job.
A program that's full of bugs is slower still. It doesn't work.
Well,
so it's
well, the thing was, I wasn't selling him. I tried to tell him, I wasn't saying write the driver in BASIC, write the menus in BASIC, because they had Visual Basic at that point. Now, it may be that there was no way to do FFI with Visual Basic. I don't know. But he was worried about the speed of the menus in Visual Basic.
Yeah, but so that's
yeah. Well, even not with menus, even with core algorithms. So something that is, I mean, people say, well, this is one story that happened, for one particular customer. No. It's actually something that repeats over and over. So when you try to do something in Smalltalk and you say, yeah, it's just we're just gonna do a prototype, to get the concepts right. And the guy kind of buys it, right? And then says, yeah, okay, we'll do the prototype and then we will rewrite the thing in C++ so it will be actually fast. And because I like it has repeated so many times, so I said, yeah, okay, let's do that. And so with this guy, but it's really repeated many times. So we do the system in Smalltalk, and it's pretty fast. It's plenty speed to be acceptable. And then they said, yeah, but we already hired the C++ programmers. And okay, well, my consulting job ends at this point. You do whatever you want. Okay. 6 months later, they call me, super surprised. Hey, Boris, we're trying to understand what's going on. Can you come and help us? We re-implemented this thing, and on real customer data, this thing is 10 million times slower than our Smalltalk prototype. How can it be? And I look at what they did, and from an algorithmic perspective, like there is some sorting stuff going on, and they just programmed in C++, they just re-implemented bubble sort. Whereas, you know, it's properly in Smalltalk, it's all, and I see a bunch of spaces where a bunch of places where they just access things by linear search and all that crap. So we take one example of like the guy just doesn't understand. How can it be? I implemented it in C++ and it's 10 million times slower. Yeah, but look, there's this thing called hashing. That's why you don't go do a linear search. And he doesn't understand the word hashing. He says, I don't understand what's there to cache. No, not caching, hashing. And he just blames it on my accent. And no, let me explain to you.
He thought you were talking about hashish, which is weed.
Something. So I'm like, okay, let's go very, very slowly, and let me explain to you what hashing is and how you speed up access to data using that. And I start talking, and the guy's eyes roll into like inside his skull. So I spend 20 minutes explaining the idea at an as elementary level I can, and you know, the guy doesn't get it, and he's just sleeping, snoring his eyes completely. And when I'm done after 20 minutes, and I say, okay, well, and that's it in a nutshell. The guy wakes up and goes, Boris, your academic background is showing through. So and it's all the time. It repeats that kind of thing, just repeats over and over and over and over.
So it's actually a culture thing here. The man had learned when I was 7 years old, don't do what the teacher said, don't learn anything. Learning is for stupid people. He when he was 30 years old, he could no longer get the idea that, hey, you should learn something. No, I've learned, I've been to school, I've got my driver's license, why should I learn anything?
Yeah, exactly. Yeah.
So its mindset is closed off before he even starts thinking. He doesn't want to think. That's not cool. That's not, hey, let's go drink beer, let's go do football. Nothing new in his life. Everybody loves change except for the change part.
There's an
well, Boris, he was just teaching to a high school kid. So, of course you teach, but the whole concept of learning something after you left high school is completely foreign to 95 to 99% of humanity.
Yeah.
And that's high. Yeah, you can't change that anymore. There's nothing to learn here. It's just a stupid preconception. He's got a bias. The bias is I don't want to learn anything. Yeah, then your software will be a million times slower if you don't want to learn anything.
There's an interesting example in the Lida book. So Lida was a programming language created by Timothy Budd, the same guy that created Little Smalltalk.
Yeah, I know him, yeah.
So Lida is a language that allows you to mix object-oriented, imperative, functional, and what's Prolog? What do you call it? Logic programming? Yeah. So he wanted to be able to mix and match in a program all of these things. And to explain why this would be interesting, in chapter 1 of the book, he gives an example where a student had to take a sequence of DNA and then had to find what was the longest sequence that repeated. Given a certain size, for example, 5, what 5 letters happened the most times in that thing? So he sat down and wrote a Fortran program and then started running it. But then he tested it and saw that the program would finish in about a week and a half.
Mm-hmm. Yeah.
So a friend of his said, "Oh, let me try this in APL." He said, "Well, Fortran is a compiled language. You're talking about an interpreter."
Yeah, except that. Yeah.
Slowness.
Yeah.
But she said, "Let me try anyway." So she did. She wrote the program, and her program finished in under a minute.
Mm-hmm.
And the reason why is that she basically repeated 5. For example, if the sequence that you're looking for is 5, she repeated the whole DNA 5 times, except shifted by 1. And then she treated that as a column, and then she sorted it. So she did the sort command. So now all repetitions were next to each other, and then she compared everybody with their previous. So she got all the repetitions. Then she found the longest one. And the reason why is it's really hard to sort things in Fortran. Whereas on APL, there's actually a key in the keyboard.
Yeah.
Sort. Yeah. So APL programmer will always think of trying to use sort in their solution because it's one key. Whereas a Fortran guy will have to call a library, and it's hard because your data is not in the same format that the library function asks for. So it was the difference between less than a minute and a week and a half because of the idea that the complex step, the linear search was quadratic with the length, whereas
that's another interesting conversation that happened at Camp Smalltalk 2 weeks ago with Dan Ingalls, and basically that there is the technological advance where we have faster processors.
Sorry, I just posed the general answer to this question. The answer to the question is, so why didn't he program? So people got fired in the 60s and the 70s when they said to their boss, "I'm going to think for a couple of hours before I write my program." They were fired for not being at the keyboard typing. So it's a good story by Edgar Dijkstra. Sorry for interrupting, Boris. Go ahead.
Right. So yes, that we've got the technological progress of the machines themselves getting faster and faster, right? But these are only hundreds, thousands, maybe millions of times that today, you know, at the state of the art machine today is how is it faster than, you know, how many times faster it is. But that's the trivial progress, because it is actually not much of a speed up compared to the algorithmic progress, where we would think, oh, well, this is an NP problem. Well, say, for one example, SAT, right? You know, we would 20 years ago we would say, yeah, well, SAT is definitely NP, and we have proof of that. Therefore, you know, all bets are off. We cannot do it. Well, now we have SAT solvers that can solve in 1,000 variables in a few milliseconds. Well, that 1,000 variables is 2 to the 1,000. That's 10 to 300. That's like Google squared. That is what I call an interesting order of magnitude of speed up. That allows us, you know, when you do the algorithmic speed up, that's something that allows to do things that you would completely just say, okay, well, this is completely intractable. And this basically only happened in the last 15 years. And to me, this is, I view it as important as the invention of the computer itself. You know, like before Alan Turing, let's say, okay, well, this is, you know, this is intractable because this would take, we cannot calculate it with pencil and paper. Okay, but if you have a computer, you can do certain calculations, you know, and suddenly become possible. Well, now, with SAT solvers, for example, you can solve things you would never think were possible on the computer, because it's like, okay, well, it's a search, it's a combinatorial search of a problem space 2 to several thousand, right? So it's like completely off. And yes, in general, it's untractable, but you know, the famous book by Ackerman, you know, solvable cases, right? So the practical sub problems of this, they are actually polynomial.
Okay, so